For more than a century, humans have been sending signals, building technology, and placing physical objects in space that reveal our presence. We have transmitted radio waves into space and launched spacecraft, carrying information about our species. These actions provide detectable evidence of our existence. Which of these activities could be detected by another civilization, and how likely is it that they have already detected them? Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a fascinating journey through the extraterrestrial world. When people first began experimenting with radio at the end of the 19th century, they thought mainly about sending signals across short distances, perhaps between ships or from one town to another. Nobody at the time truly considered that the same signals would also travel far beyond Earth itself, moving through the atmosphere and into outer space. Yet that is exactly what happened. Every time a radio transmitter was switched on, part of its energy was sent not only to receivers on Earth but also into the sky, continuing outward with nothing to stop it. By the early years of the 20th century, the very first radio transmissions were already escaping Earth and racing away at the speed of light, carrying with them faint whispers of human technology and culture. These signals came in many forms: ordinary radio programs, television broadcasts, and even radar beams designed to track airplanes or ships, all produced powerful waves that easily slipped past the atmosphere. The Earth has no barrier that blocks such waves from leaving. Once they are created, they naturally spread in all directions. Some of the waves are absorbed or reflected back by the ionosphere, which is a layer of charged particles high in the atmosphere, but many others find openings and continue outward into space. Over the course of more than 100 years, this constant leakage of signals has created what some scientists describe as a bubble of human-made radio noise surrounding our planet. This bubble expands outward at the speed of light, growing larger with every year that passes. To understand this better, one can think about how long radio and television have been around. The first public radio broadcasts began in the early 1920s. That means that signals from those days have now been travelling through space for more than 100 years. Light and radio waves move at about 300,000 kilometers per second. In 1 year, they can travel about 10 trillion kilometers, which is called 1 light year. After 100 years, those earliest broadcasts have spread outward in a sphere that is 100 light years across. That is an enormous distance. It means that stars and planets within that region could, in theory, pick up the faint traces of old radio shows, news bulletins, or even music that was sent into the air long before many of us were born. As technology advanced, the signals became even more complex. By the 1950s and 1960s, television had joined radio as a major source of leakage. Television signals are especially strong because they require large amounts of power to cover wide areas. The early systems were not designed to be efficient. Instead, they blasted signals outward in all directions to make sure that households with antennas could receive them. This unintentional design meant that television stations were effectively shouting into space every hour of every day. A sitcom or a news report broadcast in 1960 would not only reach viewers in the city, but would also send faint copies of itself outward toward the stars. Radar added another layer of leakage. Radar works by sending short, strong bursts of radio waves into the sky, and then listening for echoes when those waves bounce off objects such as airplanes, ships, or even raindrops. Because radar needs to reach far and be very precise, the beams are extremely powerful compared with ordinary radio or television. During the Second World War, radar became one of the most important technologies in military defense. Since then, radar installations have continued to operate around the world, often using immense amounts of energy. Every pulse of radar that leaves Earth also continues into space, contributing to the noisy cloud of human signals spreading outward. The question of how far these signals can be detected is complicated. While they do travel outward forever, they become weaker the farther they go. A television broadcast that seems strong in a local neighbourhood becomes incredibly faint after only a few light years. Beyond a certain distance, the signal blends into the background noise of the universe, making it nearly impossible to detect without extremely sensitive equipment. Some scientists believe that civilizations only a few dozen light years away might still be able to detect our strongest broadcasts, especially if they use giant radio telescopes far larger than the ones we have on Earth. Others argue that even our most powerful signals would become unreadable after just a few light years. Yet, in principle, the leakage is there, travelling outward continuously. It is interesting to think about the content of these signals. If an alien civilization were to intercept them, what would they actually hear or see? Early radio broadcasts often included music, speeches and news. For example, in the early 1930s one could hear jazz music, political addresses, or live reports of major events. If those signals have reached a star system 30 light-years away, the beings living there would, right now, be able to catch a faint version of what people on Earth were listening to in the 1930s. Similarly, television broadcasts from the 1950s would carry pictures of comedies, dramas and commercials complete with sound. Of course, whether aliens could make sense of these signals is another matter. They would need to decode the format, separate it from noise, and then interpret the strange human faces and voices. But the possibility remains that Earth has been unknowingly sending out a cultural diary for more than a century. The idea that our daily entertainment and technology might be broadcasting Earth's presence to the cosmos has fascinated both scientists and storytellers. Writers of science fiction have often imagined aliens learning about humanity through intercepted radio and television. In some tales, extraterrestrials respond to these signals, while in others they simply observe, studying us from afar. In real scientific discussions, the matter is more cautious. Researchers in the search for extraterrestrial intelligence, often called SETI, have long debated whether the leakage of radio signals represents a risk or an opportunity. On one hand, it might make it easier for advanced civilizations to notice us. On the other hand, if we prefer to remain hidden, this constant leakage could be dangerous by revealing our location. Over the years, people have tried to measure the strength of Earth's leakage compared with the general background of the universe. Space is full of natural radio waves, created by stars, galaxies, and cosmic events. Against this background, human signals are tiny. One comparison is often made. Earth's total leakage is similar to the energy of the noise created by just one small star in the galaxy, and there are hundreds of billions of stars. This means that from very far away, Earth would not stand out easily. However, if a civilization were already searching specifically near our Sun, they might be able to notice the unusual patterns of artificial signals among the natural noise. Another factor to consider is that our leakage has not remained constant. In the early to mid-20th century, the amount of radio and television broadcasting was extremely high. Powerful transmitters were built to cover wide areas, and efficiency was less of a concern. But in more recent decades, new technology has changed this pattern. Satellite television, cable systems, and digital streaming now carry much of the world's entertainment without requiring huge terrestrial transmitters. Many local stations that once blasted signals across continents have either reduced their power or shut down entirely. Mobile phones and wireless networks still use radio waves, but they are relatively low power and often designed to stay within Earth's environment. Some scientists argue that Earth is becoming quieter in terms of radio leakage compared with 50 or 70 years ago. If that is true, then the brightest part of our radio bubble may already be behind us, and the future leakage may be harder to notice. Radar, however, remains a strong source of outward signals. Military radars, air traffic control systems, and planetary radar used by astronomers to map asteroids all send powerful beams into space. These beams are much more noticeable than ordinary radio or television because they are extremely concentrated. A single radar pulse can be billions of times stronger than a normal broadcast. Even though the pulses last only a short time, they could stand out clearly to anyone with sensitive instruments. In fact, some researchers suggest that if aliens ever detect Earth's presence, it may be radar signals rather than television or radio that catch their attention first. One famous example of this discussion is the Arecibo radar in Puerto Rico, which for many years was the most powerful planetary radar in the world. It was used to study asteroids, comets, and even the surfaces of planets in our solar system. Each time it sent a beam outward, it also announced Earth's presence to the cosmos, at least in the direction the dish was aimed. Although the Arecibo Observatory collapsed in the year 2020, during its lifetime it contributed many signals to the growing cloud of human technology around Earth. Other radar systems in different parts of the world continue to do the same today. The spread of these signals forms a timeline of human history in space. Think about this. The very first weak transmissions from the early 1900s are now more than 100 light-years away. That means they have passed beyond dozens of nearby star systems, Signals from the 1950s, carrying television shows and news about the Cold War, have reached stars about 70 light-years away. Radio waves from the 1980s, carrying pop music and reports about world events, are now about 40 light-years out. Messages from the early 2000s are about 20 light-years away. At this very moment, signals from last night's radio programs or radar sweeps are just beginning their journey, still within a fraction of 1 light-year from Earth. This layered shell of information is like a constantly expanding record of our presence. The signals also tell a story of how humans use technology. A scientist listening from afar might notice that the frequency and power of broadcasts changed over the decades. They would see a burst of strong television signals during the mid-20th century, followed by a slow decline as digital methods replaced older systems. They would notice that radar pulses have been a steady feature since the 1940s. They might even detect new patterns from satellites orbiting Earth, which use certain frequencies to communicate. From this, an outsider could learn not only that Earth is inhabited, but also that its inhabitants are advancing in their technology. Of course, the idea of aliens intercepting our signals is only part of the story. There is also the question of whether humans themselves can detect the leakage from other civilizations. If other planets around distant stars have developed radio or television, their signals would also leak into space just like ours. With our current technology, however, it is very hard to detect such leakage. The signals would be too faint compared with cosmic noise unless they were extremely close, within a few light years. So far, no definite detection has been made. This has led some scientists to suggest that civilizations may not broadcast widely, or that they might quickly move to technologies that do not leak as much into space, just as humans are doing. The silence we hear might not mean no one is out there, but rather that their leakage is too weak or too brief to notice. The possibility of radio leakage has also shaped discussions about deliberate messages. While our unintentional signals have been leaking for more than a century, humans have also occasionally tried to send purposeful messages to space. These are usually short and rare compared with the daily flood of broadcasts, but they show that we are aware of the issue. The most famous example is the Arecibo message sent in 1974, which was a brief but powerful radio transmission aimed at a distant star cluster. Unlike ordinary leakage, this message was designed specifically to announce our presence and provide information. Yet in terms of sheer quantity, our accidental signals far outweigh such deliberate attempts. Looking at the overall picture, Earth has been broadcasting into space continuously for more than 100 years. The signals are spreading outward like ripples, carrying with them the story of human culture, conflict, entertainment, and science. They are weak and perhaps only detectable over limited distances, but they exist nonetheless. The bubble of human radio noise now spans hundreds of trillions of kilometers in every direction. Within that bubble lie thousands of stars, some of which may host planets where life is possible. Whether anyone there is listening, we do not yet know. Even if no one is out there to receive the signals, the very fact that they exist is remarkable. They are a byproduct of our inventions, a shadow of our presence that cannot be recalled or stopped. Every moment, as people use radar to track planes, as stations send out news updates, as satellites relay data, the wavefront of human-made radio continues to push outward into the unknown. This is one of the great unintended consequences of modern life, that in trying to communicate with ourselves, we have also become faint broadcasters to the universe. Military radar and satellite signals are among the strongest forms of human-made energy that have been sent outward from Earth, pulsing into the vast darkness of space. Unlike the softer signals from radio and television broadcasts, these military signals are built with power in mind, designed to stretch across great distances on Earth, and as a result many of them accidentally reach far beyond our planet, spilling into the cosmic ocean. Each strong pulse of radar, each beam of satellite transmission, and each burst of high-powered energy has the potential to travel for light years before fading into background noise, meaning that traces of human activity could be drifting silently through space even now, waiting for another civilization with sensitive enough instruments to notice. Radar itself was first developed in the early part of the 20th century, during a time of rising global tensions. In the years leading up to the Second World War, countries such as Britain, Germany, the United States, and others began experimenting with systems that could send out bursts of radio waves and then detect the echoes that bounce back from objects like airplanes or ships. These early systems were not just military tools, They were powerful transmitters that could produce strong, focused beams of energy. In those days, nobody thought much about what happened to radar signals once they left the battlefield, but in hindsight, these were some of the first deliberate human-made signals strong enough to be picked up across interstellar distances if an advanced civilization happened to be listening. By the time the Second World War broke out in the year 1939, radar had become a crucial part of military defense and offense. Nations built radar stations along coastlines, on ships, and later on aircraft themselves. The sheer number of radar beams being fired into the sky every second created an invisible net of energy around the planet. To the people using it, radar was a shield, a way to protect against sudden attacks and to spot incoming bombers before they reached their targets. But from another point of view, this was also Earth's first major technological footprint in space. Our planet had started to hum with strong rhythmic pulses of energy that could, in theory, travel for hundreds or even thousands of light years if they were powerful enough, and if space itself did not scatter them too much. After the war ended in the year 1945, radar technology did not disappear. Instead, it spread and grew even stronger. The Cold War between the United States and the Soviet Union pushed radar systems to new levels of power and sophistication. Both sides built early warning radar networks that stretched across continents. These systems were not just simple detection tools, they were massive, high-energy installations that blasted out pulses strong enough to bounce off objects thousands of kilometers away. In practice, they were used to detect enemy aircraft, intercontinental ballistic missiles, and other threats. But in the process, they were also producing some of the loudest signals Earth had ever sent into space. To get a sense of scale, consider the difference between a normal radio station and a military radar. A typical radio station broadcasting music or news might use tens of thousands of watts of power. That is enough to cover a large city and surrounding areas, and with a good antenna it might reach listeners hundreds of kilometers away. But a military radar installation could use millions of watts of power in a single pulse. When aimed into the sky, this kind of signal could outshine nearly all civilian broadcasts combined. And because radar often sends its energy in sharp bursts, rather than a constant flow, the signal is highly distinctive. It is a strong repeating pattern that stands out from the more random background noise of space. During the 1950s and 1960s, as the space race began, radar was joined by satellites as another major source of signals leaking into the cosmos. Satellites orbiting Earth needed to communicate with ground stations, and they did so using radio waves. Some of these transmissions were relatively weak, designed only to be picked up by Earth-based antennas, but others were stronger, especially those used for military purposes. Spy satellites, communication relays, navigation systems, and even early missile detection satellites sent down streams of data. Every time a satellite beamed a signal toward Earth, some of that energy missed its target and slipped away into space. Just like radar, these satellite transmissions traveled outward forever, carrying faint traces of human activity. By the late 20th century, satellite networks had multiplied. The Global Positioning System, for example, required dozens of satellites to cover the entire planet. Each satellite continuously broadcasted signals that allowed receivers on Earth to calculate their location. Although those signals were aimed downward and carefully designed to be relatively weak, the combined effect of many satellites meant that Earth's orbit was constantly buzzing with radio noise. And of course, military satellites often transmitted with far greater power than civilian systems, sending encrypted messages, surveillance data, and other information across continents. Much of this communication relied on highly directional antennas, but no system is perfect, and a small portion of each transmission leaked outward, another faint whisper to the stars. Military radar signals remain some of the strongest beacons Earth has ever unintentionally sent. One striking example is planetary radar, developed in the mid-20th century. Planetary radar was not designed for war but for science, yet it used the same basic technology. Scientists wanted to map the surfaces of nearby planets and moons by bouncing radar signals off them. To do this, they built some of the most powerful radar systems ever created, such as the one at Arecibo Observatory in Puerto Rico. This massive dish, completed in the year 1963, could blast radar beams with up to 1 million watts of power and then collect the returning echoes. With such a system, astronomers were able to measure the rotation of Mercury, map the surface of Venus through its clouds, and even study asteroids as they passed near Earth. But just like military radar, these beams did not stop at the target. They continued into space, strong, clear signals that might be detectable light years away. The possibility that alien civilizations could detect these radar and satellite signals has been considered by scientists who study the search for extraterrestrial intelligence, or SETI. Unlike television or radio broadcasts, which spread out in all directions and quickly grow faint, radar signals are often highly focused, meaning they can remain strong over long distances. If an alien civilization had a telescope tuned to the right frequency and happened to be in the path of one of these beams, they might notice that something unusual was coming from Earth. They would not necessarily understand the meaning of the signal, since radar pulses are designed for reflection rather than communication, but they might recognize the artificial nature of the pattern. Regular high-powered bursts of radio energy do not usually come from natural sources, so the detection of such a signal could raise questions about the presence of technology. The Cold War years, from the 1950s through the 1980s, were especially noisy for Earth. Large radar systems, such as those used in the Ballistic Missile Early Warning System, were designed to detect incoming missiles from thousands of kilometers away. These installations often used very high frequencies and very strong pulses, which would have spilled into space in great amounts. At the same time, both the United States and the Soviet Union launched fleets of satellites for surveillance, communication, and navigation, many of which relied on constant radio links. In effect, Earth was shining brightly in the radio spectrum, especially in the bands used for radar and military communication. It is worth noting that signals do not remain strong forever as they travel through space. The farther they go, the more they spread out and fade. After a few dozen light years, even the most powerful radar pulse becomes difficult to distinguish from background noise. But the sheer strength of some transmissions means that they could remain detectable for significant distances. For instance, a 1 million watt radar pulse focused into a narrow beam could, in theory, be noticed by a civilization with advanced radio telescopes even hundreds of light years away. This is not guaranteed, since much depends on the sensitivity of their instruments and whether they happen to be in the right place at the right time, but the possibility remains. In the 21st century, the nature of signals leaking from Earth has shifted somewhat. Civilian broadcasts, such as traditional television and radio, are less powerful than they once were, as more communication has moved to fiber optic cables, satellite links, and digital networks. However, military radars and satellites continue to produce strong emissions. Modern missile defense systems, for example, rely heavily on radar to track fast-moving objects in space. These radars are extremely powerful, designed to detect small targets thousands of kilometers away. Similarly, space surveillance networks use radar to keep track of debris and satellites in orbit, ensuring that collisions can be avoided. Every one of these operations adds another layer to the invisible cloud of radio energy surrounding Earth. Some scientists have even argued that our strongest and most easily detectable signals are not the intentional ones, like the Voyager Golden Record or the Arecibo message, but rather these unintentional military transmissions. While we have carefully crafted a few symbolic messages to send outward into space, they are rare and limited. In contrast, radar and satellite signals are constant, powerful, and widespread. They may not carry much meaningful content, but they do reveal something very important: the presence of technology on Earth. To another civilization searching the skies, that could be all the evidence they need to conclude that they are not alone. Another important point is that radar and satellite signals can sometimes cover a wide range of frequencies. Natural sources such as pulsars or quasars usually emit energy in more predictable ways. Artificial signals, especially radar pulses, stand out because of their sharpness, repetition, and narrow frequency bands. This makes them relatively easy to identify as non-natural, even without knowing what they are meant to do. In fact, SETI researchers sometimes use radar signals from Earth as test cases, training their systems to recognize artificial patterns in the noise of the cosmos. If humans can spot their own radar leaking into space, it stands to reason that others might too. Looking ahead, it seems likely that radar and satellite signals will remain a major part of Earth's technological footprint. As space exploration continues, more satellites will be launched, each sending streams of data across the void. As military needs evolve, new radar systems will be built, some possibly even stronger than the ones we have today. With every pulse and every transmission, Earth adds another tiny signal to the vast conversation of the universe, even if we never intended to join it. And whether or not anyone else is listening, those signals will continue to travel outward for millions of years, carrying with them the unspoken evidence of human civilization. Earth's atmosphere is like a giant chemical fingerprint. When light from the sun passes through it, certain gases leave very clear marks, or what scientists call spectral lines. These are not just random patterns, but meaningful signals that reveal what our planet is made of. For a long time, astronomers have studied this fingerprint carefully because it contains many important details about life on Earth. The mixture of gases floating above our heads is not something that would easily occur by chance. Instead, it is shaped by biological activity, which means the existence of living things, plants, animals, and microbes that together produce and consume gases in a way that creates balance. This is why astronomers often describe the atmosphere of our planet as a biosignature, a living sign that can be recognized from far away. When scientists talk about biosignatures, they usually mean certain gases like oxygen, methane, ozone, nitrous oxide, and even combinations of gases that do not easily exist together unless life is involved. Oxygen is the most famous of these because it makes up a large part of Earth's air and is essential for breathing. But oxygen does not remain stable in an atmosphere for very long unless something keeps producing it. In our case, plants, algae, and some microbes constantly release oxygen into the air through photosynthesis. Without this ongoing biological activity, oxygen would quickly react with other chemicals and disappear. This means that if an alien astronomer somewhere across the galaxy looked at Earth with powerful instruments, they would notice oxygen's strong fingerprint and might guess that something alive is present here. Methane is another important piece of the puzzle. On Earth, methane is produced by living things such as microbes that live in wetlands, animals that release it during digestion, and human activities like farming and energy production. It can also come from natural non-living sources such as volcanoes or chemical reactions deep underground, but these usually do not produce enough to explain the levels we see. What makes methane special as a biosignature is the way it behaves when it exists alongside oxygen. Normally, oxygen and methane destroy each other quickly through chemical reactions. If they were left alone, the atmosphere would not hold both of them at the same time for long, but on Earth, they coexist because life keeps pumping both gases into the air. This unusual balance is one of the strongest clues that our atmosphere is being maintained by biological activity. Ozone, which is made of 3 oxygen atoms, is another key marker. It forms naturally when ultraviolet radiation from the sun interacts with ordinary oxygen molecules. Ozone plays a protective role by blocking harmful ultraviolet rays that could damage living cells. Because ozone is directly tied to oxygen, detecting it around a distant planet can serve as an indirect way of confirming the presence of oxygen itself. In fact, ozone creates very clear signals in the infrared part of the spectrum, which telescopes can pick up from far away. Nitrous oxide, often called laughing gas on Earth, is also a potential biosignature. It is mainly produced by microbes in soils and oceans, and like methane, it would not build up to noticeable levels without continuous biological activity. When scientists study exoplanets, which are planets outside our solar system, they often look for these same gases. The method involves capturing starlight that passes through a planet's atmosphere during a transit, when the planet crosses in front of its star. As the light filters through, molecules in the atmosphere absorb specific wavelengths, leaving behind unique patterns. By analysing these patterns with a tool called spectroscopy, astronomers can figure out what gases are present. This is not easy because the signals are faint, and many different factors can confuse the results, such as clouds, dust, or even the star's own activity. But with modern telescopes and future ones being planned, the ability to detect biosignatures is becoming more realistic. The idea of looking for Earth's atmospheric signature is not just about studying other worlds, it is also about understanding how our own planet looks from a distance. Astronomers sometimes call Earth the control case, because it is the only planet we know that has life. By pointing satellites or even instruments on the Moon toward Earth, scientists have studied how our planet's gases appear as though we were observing it from light years away. These experiments have confirmed that oxygen, methane, and ozone stand out strongly, especially when viewed in the right parts of the spectrum. This helps scientists prepare for what to expect when they eventually study truly Earth-like planets around other stars. The history of Earth's atmosphere also tells a fascinating story about life. Billions of years ago, Earth did not have much oxygen at all. The early atmosphere was mostly made of carbon dioxide, nitrogen, water vapor, and other gases released by volcanic activity. Life at that time consisted of microbes that did not need oxygen to survive. Then, around 2.5 billion years ago, something extraordinary happened. Photosynthetic microbes, known as cyanobacteria, began producing oxygen in large amounts. This event, called the Great Oxidation Event, gradually filled the atmosphere with oxygen. At first, most of it reacted with rocks and minerals, but eventually the gases built up to levels that reshaped the entire planet. This allowed new forms of life to evolve, including the ancestors of animals. The presence of oxygen also gave rise to the ozone layer, which shielded the surface from harmful radiation and made it safer for life to expand. If extraterrestrial astronomers had looked at Earth before this event, they might not have noticed any strong biosignatures. The planet could have seemed lifeless even though microbes were thriving. Only after oxygen rose to significant levels would Earth's fingerprint become clearly biological. This is an important lesson for scientists today. A lack of oxygen in an exoplanet's atmosphere does not automatically mean no life exists. It could mean life is present, but in a form that does not produce large amounts of oxygen, or that the planet is in an earlier stage of evolution. This is why scientists talk about a range of biosignatures instead of just one gas. A full picture requires looking at multiple gases and their interactions. For example, if a planet has carbon dioxide and water vapor but no oxygen, it might still support microbial life similar to early Earth. If a planet has methane without oxygen, it could be explained by geological processes, but if methane and oxygen appear together, the case for biology becomes much stronger. Scientists are also considering more unusual biosignatures, like certain sulfur gases or even pigments that life might use to harvest energy. These would create distinctive patterns in light that could, in principle, be detected with powerful telescopes. The challenge is separating true biosignatures from false ones. Some chemical combinations might look like signs of life but actually come from non-living processes. For instance, oxygen can sometimes build up in a planet's atmosphere without life, if ultraviolet radiation splits water molecules and the hydrogen escapes into space, leaving oxygen behind. Similarly, methane could come from volcanic activity rather than microbes. This means astronomers have to be cautious and look at the broader context of the planet, including its star type, temperature, geological activity, and potential for water. Only by putting all these clues together can they make a convincing case for life. The excitement around Earth's atmospheric signature has grown stronger with the arrival of new telescopes. Instruments like the James Webb Space Telescope, launched in the early 21st century, are already beginning to examine exoplanet atmospheres in greater detail. Webb's ability to observe in the infrared makes it especially good at spotting molecules like carbon dioxide, methane, and water vapor. Future telescopes, both on the ground and in space, are being designed to go even further, with the goal of detecting oxygen and ozone on Earth-sized planets orbiting Sun-like stars. Missions such as LUVOIR or HABEX, which are still in the planning stages, could one day directly image Earth-like planets and search for biosignatures with unmatched precision. The possibility of finding an Earth twin with the same atmospheric fingerprint is one of the most thrilling scientific pursuits of our time. If astronomers ever detect oxygen and methane together on a distant planet, it would immediately spark intense debate and excitement. While there would still be the need to rule out non-biological explanations, such a discovery would be the closest thing to evidence of life beyond Earth. It would also raise profound questions about how common life is in the universe and whether our planet is unique or just one example among many. The study of Earth's atmospheric signature also connects to climate science and our own survival. By observing how gases in the atmosphere change over time, scientists can understand how human activities are altering the balance. For instance, carbon dioxide levels have risen sharply due to burning fossil fuels, and methane levels have also increased because of agriculture and industry. These changes affect not only Earth's climate, but also how the planet would appear to distant observers. In theory, an alien civilization with advanced instruments might even detect unusual increases in greenhouse gases and wonder whether Earth is undergoing industrial activity. This idea has led scientists to propose the concept of technosignatures, signals not just of life but of technology. Earth's biosignature is not static. It has changed through history and will continue to evolve in the future. If humanity survives for millions of years, our planet may develop very different atmospheric characteristics depending on how our civilization uses energy and resources. Even if humans disappear, life itself will continue to shape the atmosphere in new ways. This dynamic nature means that detecting biosignatures on other planets is not about finding a perfect copy of modern Earth, but about recognizing the chemical fingerprints of life in many possible forms. One fascinating experiment involved using data from spacecraft that looked back at Earth as though it were an exoplanet. When the Galileo spacecraft flew past Earth in the late 20th century, it used its instruments to analyze the spectrum of our planet's light. The data showed strong signs of oxygen, methane, and vegetation, which the mission scientists described as clear evidence of life. This was the first real demonstration of how life on a planet could be detected from far away. Since then, other missions like Epoxy have also turned their instruments back toward Earth to refine these techniques. Another creative method scientists use is called the red edge. Plants on Earth reflect light in a special way at near-infrared wavelengths. This sharp change in reflection, known as the vegetation red edge, could in theory be detected on a distant planet if it has widespread plant-like organisms. While this is much harder to measure than gases, it adds another possible clue in the search for life. If both atmospheric biosignatures and surface signatures like the red edge were observed together, the evidence would be even stronger. The study of biosignatures also forces us to expand our imagination about what life might be. Life elsewhere might not resemble Earth life exactly, and its atmospheric fingerprints could be different. For instance, a planet with life based on different biochemistry might release gases we do not commonly associate with biology. This is why scientists are cautious not to limit themselves only to Earth-like markers. At the same time, Earth's signature remains the most reliable starting point, because it is the only proven example we have. The idea of Earth's atmospheric signature has influenced culture and philosophy as well. It highlights the interconnectedness of biology, geology, and chemistry in shaping our world. It reminds us that the air we breathe is not just a background condition, but a living record of all the processes happening on the planet. Every breath of oxygen we take is a result of countless generations of microscopic organisms that transformed Earth billions of years ago. The fact that this transformation can be detected across interstellar distances is both humbling and inspiring. Artificial light pollution, also called Nightside illumination, is one of the most striking ways in which our planet stands out when seen from a distance. Unlike the natural glow of the sun reflecting on the Earth during the day, or the soft silver light of the moon at night, this brightness is made by humans. It is the glow of billions of lamps, streetlights, stadium lights, neon signs, office towers, factories, vehicles, and countless other artificial sources that together paint the surface of the world with a permanent glow. Long ago, before electricity became common, the Earth's night side was dark except for natural lights like stars, the moon, and small patches of fire from volcanoes or lightning storms. But in the last 2 centuries, the story changed in a dramatic way. The invention of electric lighting in the 19th century changed how people lived, worked, and organized their societies. When Thomas Edison and Joseph Swan perfected practical electric light bulbs in the 1870s and 1880s, nobody could have predicted just how much of the Earth's future appearance would be reshaped. At first, only a few homes, theatres, and factories used electric lamps. By the early 20th century, cities in Europe and North America began installing electric street lamps. Within a few decades, these glowing points of light grew into a connected web of bright lines across city streets. What had once been dim towns became glowing clusters visible from the sky. By the mid-20th century, satellites launched into orbit showed the first images of Earth at night. Those pictures revealed glowing continents surrounded by dark oceans, with cities blazing like constellations on the surface. As the population of the planet kept increasing and technology spread, so too did the glow of artificial light. By the early 21st century, about 4 out of every 5 people in the world were living under skies polluted by artificial light. Entire regions of Earth were no longer able to see the Milky Way because the brightness of city lights drowned it out. From the perspective of space, the night side of Earth is a patchwork of dazzling lights, dense in urban areas and scattered in rural ones. Astronauts aboard the International Space Station often describe this glow as breathtaking. Cities like New York, Tokyo, Paris, Lagos, Cairo, and Sao Paulo are so bright that their outlines are easy to recognize from hundreds of kilometers above. Artificial light pollution can be divided into several forms, but all of them contribute to this global glow. One type is called sky glow, which is the dome of brightness above cities caused by light scattering in the atmosphere. Another is glare, which happens when light is too strong for the eyes to handle comfortably. Then there is light trespass, when unwanted brightness spills into places it was never meant to reach, like a street lamp shining into a bedroom window. Finally, there is clutter, which refers to the chaotic mix of too many bright sources packed together, often along highways or in advertising districts filled with signs. All of these forms blend together and make the night side of Earth brighter than it was ever meant to be. From afar, light pollution has made Earth look like a planet wrapped in glowing necklaces. Satellite maps reveal fascinating patterns, long threads of light that trace highways connecting one city to another, bright dots scattered in deserts where oil fields are illuminated, and faint glowing clusters in otherwise dark regions where towns or mining sites exist. In the Middle East, flames from gas flares in oil extraction fields create permanent spots of brightness. In Siberia, small settlements stand out in the snow-covered darkness. Across Africa, the contrast is striking, with coastal cities like Lagos and Cairo shining brilliantly, while vast inland areas remain almost completely dark. In South America, the Amazon basin is mostly black, but bright chains of light outline cities along the coasts and rivers. Artificial light pollution has many consequences on Earth itself, beyond how it looks from space. Humans, animals, and even plants are affected by the constant brightness. For people, too much light at night disrupts natural sleep cycles, making it harder to rest. Studies have linked excessive exposure to artificial light at night with health issues such as insomnia, stress, and even increased risks of certain diseases. For wildlife, the problem can be even worse. Sea turtles, for example, hatch on beaches and normally crawl toward the ocean guided by the reflection of the moon and stars on the water. But when beaches are crowded with hotels and streetlights, baby turtles often crawl inland toward the lights, where they die. Birds are also confused by bright cities. Many migratory species navigate by the stars, and glowing skylines cause them to circle endlessly, crash into buildings, or collapse from exhaustion. Insects too are drawn to artificial light, sometimes in such large numbers that their populations are threatened because they waste energy circling lamps instead of feeding or reproducing. From a scientific viewpoint, one of the greatest losses caused by light pollution is the disappearance of the natural night sky for millions of people. For most of human history, every culture studied the stars. The Milky Way was a common sight, and countless myths, calendars, and navigation systems were based on it. Today, in many cities around the world, children grow up never seeing the Milky Way at all. Astronomers also face serious challenges because telescopes near populated areas struggle with the brightened skies. Some of the largest observatories on Earth, such as those in Chile or Hawaii, were built in remote areas to avoid light pollution. Yet even those regions are beginning to feel the effects as human activity expands. Looking at Earth from space, it is clear that the brightness is unevenly distributed. In Europe, for example, the entire continent seems like a solid sheet of light stretching from London to Rome. In Asia, dense networks cover eastern China, South Korea, and Japan, making them among the brightest places on Earth at night. In North America, the East Coast from Boston to Washington forms a giant glowing corridor. By contrast, the interiors of places like Canada, Mongolia, or the Sahara Desert remain very dark, highlighting how human settlement shapes the planet's appearance. This uneven pattern is important because it shows where human activity is most intense and where natural darkness still survives. Artificial light pollution has even been suggested as one of the potential biosignatures that alien civilizations might detect. If another advanced society were watching Earth with telescopes sensitive enough, they could notice the strange glow on the dark side of our planet. Natural processes like lightning or volcanoes can create flashes, but the steady, widespread glow of city lights is something different. Scientists have even studied how future telescopes might be able to spot similar signs on exoplanets. For instance, if a faraway planet showed unusual night-side brightness, it might be evidence that intelligent beings there also developed artificial lighting. In this way, the very thing that causes problems for our ecosystems could also be a beacon announcing our presence to the galaxy. The growth of artificial lighting has also been tied to culture, economy, and politics. Wealthier regions often shine brighter because they have more infrastructure, more roads, more industries, and more resources to power countless lights. Poorer regions, on the other hand, may appear much darker, not necessarily by choice but because of limited access to electricity. This creates a visible map of inequality when seen from above. The differences are so sharp that researchers sometimes use nighttime satellite images as a way to estimate economic development. For example, the border between South Korea and North Korea is one of the starkest contrasts visible from space. The southern side is brightly lit while the northern side is almost entirely dark. Even though artificial light pollution seems permanent, it is not without solutions. Many cities have started projects to reduce their glow, switching to energy-efficient lamps that direct light downward instead of scattering it upward helps reduce sky glow. Some places enforce dark sky policies, requiring that businesses and homes use shielded lighting. In certain areas, festivals celebrating the beauty of darkness encourage people to turn off their lights for a few hours so that stars can be seen again. These steps not only save energy and money, but also restore something precious that has been lost, the natural beauty of the night sky. When considering the long history of human civilization, the change is staggering. For thousands of years, nights were mostly dark except for firelight. Campfires, torches, and oil lamps created small circles of brightness, but the sky always dominated. The transformation began slowly with gas lamps in the 18th and 19th centuries. When electricity spread in the 20th century, the scale of brightness grew beyond imagination. Now, in the 21st century, we live in a world where even remote corners are often touched by the glow of human activity. In a way, Earth itself has become a glowing planet, half dark and half covered by a web of lights. The brightness of artificial light pollution continues to expand as new technologies spread. LED lights, which became common in the early 21st century, are efficient and long-lasting, but because they are so cheap, they are often overused. Instead of reducing light pollution, in many cases they made it worse because more lamps were installed. Billboards, sports arenas, and shopping centres now use powerful LED panels that shine brighter than older bulbs ever did. As a result, the total glow of Earth keeps increasing year by year. Some studies show that the area of the planet affected by artificial night brightness is growing by more than 2% every year. This means that the problem is not slowing down, but still accelerating. For space travellers, however, the sight of Earth's night side is unforgettable. Astronauts often describe the moment when the spacecraft moves from the daylight side to the dark side. Suddenly, instead of black emptiness, the planet glows with countless lights, almost like another kind of sunrise. They can trace entire continents, spot the shining coastlines, and even identify individual cities from hundreds of kilometers above. For them, it is both a source of pride and a reminder of the environmental cost of modern life. Artificial light pollution is also used in scientific studies in unexpected ways. For example, measuring the glow of lights from space helps track urban expansion. In regions where census data is weak or outdated, satellite images of nighttime brightness provide clues about population growth, energy use, and even migration. Human activity leaves clear traces in the night sky, and researchers can measure them with remarkable accuracy. During natural disasters, changes in nighttime light also provide rapid information. After major earthquakes, floods, or power outages, satellites detect sudden drops in brightness, helping emergency teams understand the extent of the damage. The contrast between natural darkness and artificial brightness is perhaps one of the most important themes of this subject. Darkness is not just the absence of light. It has ecological, cultural, and emotional importance. Many species depend on darkness for their survival, and human beings also need it for their health. Yet modern societies often treat darkness as a problem to be solved with more lamps. By flooding our world with artificial brightness, we may have overlooked the value of the night itself. Seen from afar, Earth is unlike any other planet in our solar system because of this glow. Venus is wrapped in thick clouds and reflects sunlight but does not glow at night. Mars is dusty and dry, with no artificial brightness. Jupiter and Saturn shine with storms and auroras, but those are natural phenomena. Only Earth shows the steady, organized glow of city lights, outlining continents and coastlines. This glow is perhaps one of the clearest signs of intelligent life on the planet, visible from thousands of kilometers away. The expansion of artificial light pollution shows no sign of stopping soon, but awareness is growing. People in many parts of the world are beginning to rediscover the beauty of darkness. Movements promoting dark sky preserves have led to protected areas where artificial light is strictly controlled. In these places, the Milky Way can once again be seen in its full glory. Children and adults alike can experience the kind of night sky that our ancestors saw for millennia. The challenge is balancing the real benefits of artificial light, such as safety and economic activity, with the need to preserve natural darkness. Industrial pollution markers are one of the strongest and clearest indicators that intelligent life has developed technology on a planet. When scientists on Earth study the atmosphere of our own planet, they notice chemicals that would never appear naturally in large amounts without human activity. These substances are not the result of volcanoes, forest fires, or natural cycles of the oceans and skies. Instead, they are the products of factories, machines, refrigeration systems, aerosols, plastics, and many other human inventions. The presence of these strange chemical fingerprints is like a silent signal that tells the story of technology. If astronomers on another world were to look at Earth from afar and analyze the light passing through our atmosphere, they would see gases like chlorofluorocarbons, usually shortened to CFCs, and many other compounds that are not natural. These chemicals could not be explained unless they knew that some kind of industrial civilization was at work. The story of industrial pollution is closely tied to the rise of technology on Earth. During most of human history, the air was shaped by natural processes, oxygen produced by plants, carbon dioxide released by breathing and fires, nitrogen making up the bulk of the sky, and smaller amounts of gases like methane and ozone. When humans lived in small numbers, their effect on the atmosphere was too small to change the global balance. Even when people began farming thousands of years ago, cutting down forests and planting crops, the chemical signs were still relatively minor compared to the vast size of the atmosphere. But all of this began to change when humans entered the era of machines. With the Industrial Revolution that began in the late 18th century and gathered speed through the 19th and 20th centuries, humanity started burning massive amounts of coal, oil, and natural gas. This burning released not only carbon dioxide but also countless other chemicals, including sulfur compounds, nitrogen oxides, and artificial molecules designed in laboratories. One of the most important of these molecules was the family of substances known as chlorofluorocarbons. They were created in the early 20th century, first developed in the 1920s and 1930s, when scientists were searching for safer refrigerants. Before that, refrigerators and cooling systems often used dangerous chemicals like ammonia or sulfur dioxide, which could cause injuries or even deaths if they leaked. When CFCs were invented, they seemed like a miracle, stable, non-toxic, and highly effective at cooling. They were used not only in refrigerators but also in air conditioners, aerosol sprays, foam production, and many other applications. For decades, nobody suspected that these stable molecules could cause any harm. They were released into the air and slowly drifted upward into the atmosphere. It was not until the 1970s and 1980s that scientists realized CFCs were damaging the ozone layer high in the stratosphere. The ozone layer is a thin shield of gas that blocks harmful ultraviolet radiation from the sun. Without it, life on Earth would be exposed to dangerous rays that could cause cancer, harm crops, and damage ecosystems. Researchers discovered that when CFCs reached the stratosphere, they were broken apart by sunlight, releasing chlorine atoms that destroyed ozone molecules. Each chlorine atom could break apart thousands of ozone molecules before being neutralized. The result was a thinning of the ozone layer, especially over Antarctica, where the so-called ozone hole was first detected in the 1980s. This discovery shocked the world. For the first time, humanity realized that an artificial chemical created in laboratories could have global effects on the entire planet's atmosphere. Governments came together to sign the Montreal Protocol in 1987, an international treaty that phased out the production of CFCs and other ozone-depleting substances. This was one of the rare moments when humanity responded quickly and decisively to an environmental crisis, and it has had success. Since then, the levels of CFCs in the atmosphere have slowly decreased, and the ozone layer is showing signs of recovery. Still, traces of these chemicals remain, and some are still detectable decades after their use has been banned. Now, imagine scientists on another planet, many light years away, pointing their telescopes at Earth. If they had sensitive instruments capable of breaking down the spectrum of light passing through Earth's atmosphere, they might notice the chemical fingerprints of CFCs. These fingerprints are unique because no natural process produces them in such quantities. Unlike carbon dioxide, which can come from volcanoes or natural fires, or methane, which can be produced by microbes, CFCs are purely artificial. Their presence would be a strong indication that Earth is home to a technological civilization. This is why astronomers today often discuss industrial pollution markers when talking about the search for extraterrestrial intelligence. We're used to thinking about radio signals, giant telescopes, or spacecraft as the main ways of finding alien life. But another way could be to detect signs of industrial chemistry in an exoplanet's atmosphere. If a distant planet shows the presence of CFCs, hydrofluorocarbons, or other complex synthetic chemicals, it might be the smoking gun that points to the existence of industry. It would be very difficult to explain such signals without intelligent beings creating them. On Earth, CFCs are just one example. Humanity has filled the atmosphere with many other substances that act as industrial fingerprints: nitrogen oxides, sulfur compounds, halogenated hydrocarbons, and even microplastic particles now float through the skies and waters of the planet. While some of these chemicals can occur naturally in small amounts, the massive quantities released by human activity make them unusual. If another civilization were to look carefully, they might be able to detect the excess levels of these compounds and realize they are signs of technology. The broader idea here is that a planet's atmosphere acts like a record of everything that happens on its surface. Volcanoes leave their mark with sulfur and ash. Oceans and living organisms release gases like methane and oxygen. And intelligent civilizations leave behind their artificial chemistry, which lingers in the sky long after it's created. The atmosphere becomes like a library of history, showing what forces are at work. In the case of Earth, the record is clear. Our atmosphere carries the marks of both life and technology. Some scientists have even proposed that industrial pollution markers could outlast the civilization that created them. For example, if humanity were to disappear tomorrow, many of the artificial molecules we have released would remain for decades or centuries. CFCs can last in the atmosphere for about 100 years. Other fluorinated gases can persist for even longer, some surviving for thousands of years. This means that long after a civilization is gone, its chemical traces could still be visible to a careful observer. A telescope many light years away could detect the fingerprints of a civilization that vanished long ago. In this way, industrial pollution markers could serve as a kind of time capsule, preserving the memory of a technological society even after its end. On Earth, industrial pollution is often discussed as a danger and a challenge. It affects human health, ecosystems, and the global climate. But when seen from the perspective of space exploration and the search for life beyond Earth, these same pollutants become signals. They become proof that we have reached a stage of technology where our activities are powerful enough to reshape an entire planet. For astronomers looking outward, these signals may be one of the best chances of finding others like us. If we think about what it would mean to detect CFCs or other artificial chemicals on a distant planet, the implications are enormous. It would suggest that intelligent life not only exists but has advanced far enough to develop industries. It would also suggest that they use similar kinds of chemistry to ours, perhaps because the challenges of refrigeration, energy, or materials are universal. Of course, such a discovery would raise many questions. Is that civilization still alive? Or are we only seeing the ghost of its former presence? Are they facing the same environmental challenges we do, struggling with pollution and climate change? Could they be aware that their chemical fingerprints are visible across the stars just as we're beginning to realize now? When astronomers design telescopes to study exoplanet atmospheres, they are not only looking for natural biosignatures like oxygen and methane, they're also preparing to look for technosignatures, evidence of technology. Industrial pollution markers are one of the most promising kinds of technosignatures because they are specific and hard to explain away. Detecting radio signals might be difficult because they fade quickly and require the right frequency at the right time. But pollution markers can linger in the atmosphere for centuries, making them easier targets for detection. The James Webb Space Telescope, launched in the early 21st century, is already capable of studying the atmospheres of some exoplanets. It can look for water vapor, carbon dioxide, methane, and other molecules. In the future, even more powerful instruments may be able to search for rarer and more complex chemicals, including artificial pollutants. This opens the possibility that in the coming decades, we might detect signs of alien industries. If we were to find a planet with CFCs or other industrial gases, it would change our understanding of the universe forever. It is worth noting that not all industrial markers are equally visible. Some molecules break down quickly in the atmosphere, while others are more stable. For example, carbon dioxide is abundant and long-lasting, but it can be produced naturally as well as artificially, so it is not a reliable marker of industry by itself. On the other hand, fluorinated compounds are almost entirely artificial and remain stable for long periods. These are the kinds of molecules scientists are most interested in when thinking about detection from afar. Another factor is the size of the civilization and its level of industrial activity. A small population with limited industry might not release enough chemicals to be noticeable from light years away. It is the large-scale burning of fuels, mass production, and widespread technology used that make these markers detectable. On Earth, the global spread of industry over the past 2 centuries has created a strong signal. If another civilization followed a similar path, its atmospheric changes might also become visible once its industry reached planetary scale. There is also a sobering aspect to all this. Industrial pollution markers do not just reveal the presence of technology, they also reveal its costs. On Earth, these pollutants have caused serious harm to the climate, the ozone layer, and ecosystems. If we were to find similar markers on another world, it might suggest that alien civilizations face the same struggles. Pollution might be a universal stage in the development of technology. Perhaps every civilization that reaches a certain level of advancement goes through a period of releasing harmful chemicals before learning to manage or replace them. This raises questions about survival. Can civilizations overcome the challenges posed by their own pollution, or do some of them fail and collapse under the weight of their own industries? The story of Earth offers both warnings and hope. On one hand, our industrial activities have caused global warming, air pollution, and the destruction of habitats. On the other hand, we have shown that international cooperation can work, as seen in the success of the Montreal Protocol. If we could recognize the danger of CFCs and act to reduce them, perhaps other civilizations could too. Detecting pollution markers on another planet might not only reveal their presence, but also give us a glimpse into their struggles and choices. In thinking about industrial pollution as a signal, it becomes clear how interconnected everything is. The molecules released in a factory smokestack or an air conditioner do not simply vanish. They spread across the globe, mix into the air, and rise into the atmosphere. From there, they can persist for decades, reflecting and absorbing light, altering the climate, and even becoming visible across interstellar distances. The act of releasing these molecules becomes an unintentional broadcast, a message sent without words, announcing the existence of technology. On Earth today, we continue to add new substances to the atmosphere. Modern industries release hydrofluorocarbons, perfluorocarbons, sulfur hexafluoride, and many other exotic compounds. Some of these are replacements for older ozone-depleting chemicals, but they still contribute to global warming and are long-lived. In fact, some of these gases are thousands of times more powerful than carbon dioxide at trapping heat. This means they are not only dangerous for our climate, but also very visible in a planetary spectrum. If another civilization is looking, these are exactly the kinds of fingerprints they might detect. Beyond gases, there are also other forms of industrial markers. For example, scientists have found microplastic particles in the atmosphere, carried by winds across oceans and continents. These tiny pieces of plastic are created when larger plastic waste breaks down. They can now be found on mountaintops, in deep ocean trenches, and even in human bodies. While it's harder to imagine detecting microplastics from light years away, their widespread presence shows just how much technology reshapes the environment. If advanced telescopes become sensitive enough, even solid particles like these could one day serve as signals. Some researchers also suggest looking for unexpected chemical balances in atmospheres. On Earth, the rapid increase of carbon dioxide since the 19th century is clear evidence of industrial activity. If astronomers were to see a similar rise in greenhouse gases on another planet, they might suspect technological causes. While natural events like massive volcanic eruptions could also explain such changes, the sustained and accelerating trend would hint at industry. The idea of industrial pollution markers adds a new layer to the search for life. Instead of only asking whether life exists, we can ask whether technology exists. And instead of only asking whether a civilization exists now, we can ask whether it once existed. Because the fingerprints of industry may remain long after a civilization is gone, they may be one of the most enduring signs of intelligence in the universe. Large-scale energy use is one of the clearest signs of advanced activity on a planet, because when people or any other form of intelligent life make machines, build cities, and power industries, they need to consume vast amounts of energy, and energy never disappears without leaving behind some kind of trace. According to the basic laws of physics, energy cannot be created or destroyed, it can only be transformed. Every time a machine runs, a light glows, or an engine turns, not all of the energy is used in a perfectly efficient way. A large part of it always becomes waste heat or other byproducts that escape into the surroundings. That leftover energy spreads outward in ways that could, at least in theory, be noticed from far away. If a civilization on Earth can detect heat emissions from space using telescopes and instruments, then a civilization elsewhere could also look for the excess heat given off by industrial activity here. The energy that modern humanity uses is immense compared to the natural background of our world. A single household today may use more energy in one day than an entire village did several hundred years ago. When we add the consumption of millions of households, factories, transportation systems, and digital devices, the total amount becomes staggering. For example, in the early 21st century, the yearly energy consumption of the human population of Earth was measured in the order of hundreds of quintillions of joules. If we express this in simpler terms, it is as if every second humanity is releasing energy equal to millions of tons of burning coal or countless rivers rushing at full strength. That amount of energy cannot be hidden, because it always flows back into the environment in one form or another, most often as heat. If we look at cities from space with infrared sensors, we can already see how different they look compared to forests, deserts, or oceans. Cities shine not only because of lights, but also because of the heat they release. During the night, urban areas remain warmer than the countryside around them, a phenomenon known as the urban heat island effect. Roads, concrete, factories, cars, and buildings release stored energy, and in addition to that natural effect, there is the direct heat from engines, heating systems, power plants, and cooling systems. Satellites can measure these temperature differences clearly, and they show that wherever there is a concentration of people and technology, the warmth stands out against the natural background. On a much larger scale, the same principle applies to the entire planet. Earth reflects sunlight, radiates heat into space, and maintains a balance that allows life to survive. However, as industries expand and the use of energy grows, more waste heat is added to the system. This waste heat may be small compared to the energy the planet receives from the sun, but it is not zero. If human society keeps increasing its consumption year after year, eventually the waste heat becomes a measurable part of the planet's overall energy output. In fact, some scientists have calculated that if humanity continues to expand its energy use at a steady rate for thousands of years, the waste heat alone could become a global problem, raising temperatures even without the added effect of greenhouse gases. That scenario also means that from the perspective of distant observers, Earth's heat signature would start to look unusual compared to a natural planet. It is important to remember that waste heat is not the only byproduct of energy use. Whenever electricity is generated, transported, or consumed, other signals are also released. Power lines, for example, radiate weak electromagnetic fields. Machines vibrate, producing mechanical noise. Engines release chemical exhaust. But among all these byproducts, heat is the one that is impossible to avoid, because no matter how efficient a system becomes, there is always some fraction of energy that ends as heat. This makes large-scale heat emission one of the most reliable indicators of advanced activity. If another civilization were to look at Earth with advanced instruments, they would see the natural heat patterns of oceans, clouds, and land masses, but they might also notice an extra contribution that does not fit the normal picture of a planet powered only by its star. They might find that certain regions glow more strongly in infrared than expected, or that the seasonal cycle of temperatures includes strange additions not explained by climate or geography. In principle, such differences could be enough to raise suspicion that something artificial is happening. On Earth, Our technology for detecting heat signatures has already reached remarkable levels. Military satellites can pick up the launch of a missile by detecting its hot exhaust plume from thousands of kilometers away. Astronomers can map the temperature distribution of distant stars and planets using telescopes sensitive to infrared light. With instruments like these, if humanity can observe subtle details of worlds many light years away, then it is not unrealistic to suppose that other intelligent beings could do the same with even more refined technology. When people talk about energy use on a global or cosmic scale, they often refer to a classification proposed in the 20th century known as the Kardashev scale. This scale measures how advanced a civilization is based on how much energy it can harness. A Type 1 civilization can use all the energy available on its home planet, a Type 2 can use all the energy from its star, and a Type 3 can use all the energy from its galaxy. Humanity today has not yet reached even full Type 1, but it is moving in that direction. Each step upward on the scale means a vast increase in energy consumption, and with that increase comes much more waste heat. For example, a civilization that can harvest the entire power output of its star would need to build structures on a scale beyond planets, perhaps a giant shell or swarm of collectors around the star. The waste heat from such structures would radiate into space, making the star appear unusual, cooler in visible light, but brighter in infrared. Astronomers have even searched for such signs, calling them Dyson spheres or Dyson swarms, after the scientist who proposed the idea. For humanity, while we are still far from building Dyson spheres, our growing industrial footprint already leaves detectable marks. Large power plants, whether they burn coal, gas, oil, or use nuclear reactions, release heat into the environment. Cooling towers send steam into the sky, and heated water is discharged into rivers and seas. Air conditioning units in cities collectively pump huge amounts of warmth into the atmosphere. Even our digital infrastructure, from countless servers and data centers to communication networks, consumes energy constantly, and all of it eventually becomes heat. Some estimates suggest that the world's information technology sector alone consumes energy comparable to entire large nations. This means that the invisible flow of data across the globe also has a physical trace, a background warmth that accumulates. If we extend our thoughts further, the future may bring even greater markers of energy use. Suppose humanity builds massive solar farms stretching across deserts, or orbiting power stations beaming energy to the ground. Even though solar power itself does not burn fuel, the process of converting and using the captured sunlight will still end with waste heat released locally. Similarly, if fusion power becomes widespread, it may provide cleaner and more abundant energy, but the waste heat problem will remain. The more energy we use, regardless of source, the more waste heat we produce, and the easier it becomes to detect. The fascinating part of this idea is that it works both ways. If humanity can detect unusual heat emissions from distant planets, that could be a clue of another civilization's presence. Astronomers are already developing techniques to look for exoplanets, not only by their position and orbit, but also by their atmospheric composition and energy output. If a planet appears hotter than expected, or if it radiates in a spectrum suggesting artificial processes, it could be worth investigating further. Even a small deviation from natural balance might be a telltale sign. In some studies, scientists have considered whether we could identify planets whose surfaces are covered with large cities, because the energy used in lighting, industry, and transportation would warm the planet differently compared to a natural world. For instance, if a planet in the habitable zone of its star shows extra heat not explained by greenhouse gases or volcanism, it might be a candidate for artificial activity. In this sense, waste heat is like a universal fingerprint of technology. It is also interesting to note that waste heat builds up in very specific patterns. A natural planet's warmth comes mostly from absorbed sunlight and from geological activity inside. But artificial heat tends to concentrate where life and industry are most active. On Earth, this means clusters around coastlines, river valleys, and fertile plains, rather than evenly spread across the surface. This patchy distribution could itself be a sign. Observers might see that certain regions of Earth are much warmer in infrared images than they should be, even during night or winter. That contrast would not look natural. Another angle to this subject is the efficiency of technology. Engineers always try to design systems that waste less energy, but perfect efficiency is impossible. Even the best machines lose some energy as heat. For example, modern power plants may reach efficiencies of 50 or 60%, meaning nearly half of the input energy becomes waste. Electric motors, though more efficient than combustion engines, still release heat during use. Computers, which seem clean and silent, generate enormous amounts of heat that must be removed with cooling systems. Thus, the more advanced a society becomes in terms of computing, communication and automation, the more it must deal with heat management and the more noticeable its overall energy use becomes. When looking at Earth's current trajectory, one can see how the scale of energy use has exploded within just the past few centuries. In the 18th century, most of the world relied on simple biomass like wood for heating and cooking. By the 19th century, coal had become dominant, powering steam engines and factories. The 20th century saw the rise of oil, natural gas and nuclear power, multiplying the available energy many times over. By the early 21st century, renewable sources like wind and solar began contributing as well. Each step brought not only more capability but also more waste heat and more visible signs of human presence. Compared to the faint glow of ancient villages lit by firewood, today's planet glitters with countless gigawatts of artificial activity. If this trend continues for centuries, the Earth may eventually be recognizable from afar, not primarily because of its biology, but because of its technology. Even if future humanity switches entirely to renewable energy, the total amount consumed will still translate into heat. Unless humans learn to send waste heat directly into space with some kind of exotic technology, the signature will remain. Some theorists even suggest that advanced civilizations may try to manage their waste heat intentionally, arranging it in ways that are less detectable, but this would be very difficult on the scale of an entire planet. There is also the question of how much waste heat would be needed to make Earth stand out among the stars. The Sun emits about 10 to the 26 watts of power, while humanity's total energy use is on the order of 10 to the 13 watts. That means our use is still minuscule compared to the star, about 1 part in 10 trillion. From very far away, that might be hard to detect against the overwhelming brightness of the Sun. However, for a civilization with instruments more sensitive than ours, especially those focusing on infrared rather than visible light, even such a tiny difference could be noticed. And if our energy use grows by orders of magnitude in the coming centuries, the contrast would become stronger. In addition to planetary heat signatures, localized megaprojects could also become visible. Imagine a gigantic industrial facility, space-based mining operations, or a network of orbital stations transmitting power beams to Earth. These would create concentrated sources of waste heat, or unusual electromagnetic emissions that stand out sharply against the natural background. In science fiction, this is often portrayed as a beacon that could attract outside attention, whether friendly or hostile. In real science, it remains an open possibility that such large-scale activities are exactly what we should look for when searching for others. The concept of detecting civilizations through their energy use connects deeply with the broader search for extraterrestrial intelligence. For decades, the main focus has been on listening for radio signals, but as time passes, more researchers are considering indirect markers like atmospheric pollution, artificial lights, and waste heat. Unlike radio, which depends on whether a civilization wants to broadcast, waste heat is unavoidable. This makes it a more universal signal, less tied to deliberate choice, and more tied to the fundamental physics of technology. If one thinks about the far future, the ultimate expression of energy use would be a civilization so large and advanced that it covers entire planets or even stars with machinery. The waste heat from such constructs would be so vast that it could be recognized across galaxies. Some surveys of the sky have already been conducted to look for stars that are unusually bright in infrared, but so far no clear signs of mega-engineering have been confirmed. Still, the principle remains. Wherever there is large-scale energy use, there is waste heat, and wherever there is waste heat, there is a potential signal of life and intelligence. Humanity itself has begun to realize the long-term importance of energy use, not only for survival and progress, but also for how it shapes the image of Earth in the cosmos. Every light bulb, every machine, every power plant contributes to the planet's outward signature. While the numbers may still be small compared to the Sun, they are not invisible forever. One day, long after today's era, the level of activity could be so great that it changes the way Earth looks to distant observers completely. The quiet, natural planet would have transformed into a glowing beacon of technology. Planetary engineering is a term used to describe the large-scale efforts that people might attempt to change the climate or environment of an entire world. It is often linked with the idea of terraforming, which is the process of making another planet more like Earth so that humans can live there. But planetary engineering does not always mean building a new world from scratch. It can also describe the ways humans change their own planet, Earth, in such a big way that the changes can actually be seen from space. When someone thinks of environmental or climate changes, they might picture storms, melting ice, or rising seas on the surface. But when looked at on the grand scale of planetary engineering, the changes become far larger, stretching across whole continents and possibly lasting for centuries. From space, such shifts in climate or environment would not look like small details. They would appear as global patterns, vast alterations in colour, temperature, or atmospheric composition. When humans burn fossil fuels like coal, oil, and natural gas, they release carbon dioxide and other gases into the atmosphere. Over decades and centuries, these gases trap heat, and the overall climate warms. If one could step back far enough into space, Earth's glow in the infrared spectrum would change. Astronomers on another world with powerful enough telescopes might notice that Earth's energy balance is not purely natural. Instead, the temperature and the way the planet radiates heat would hint at the presence of industrial activity. These gases do not spread evenly in just a few days. It takes decades for them to build up and spread around the world. Over time, the atmosphere carries clear signs that an intelligent species has been altering its environment, deliberately or not. Even beyond the rise in greenhouse gases, humans reshape the land itself on a huge scale. Whole forests are cut down to make room for farms, cities, and roads. Deforestation is so massive that satellites orbiting Earth can record the loss of green cover. Entire regions of the Amazon rainforest, which once stretched as a nearly unbroken sea of trees, now appear as a patchwork of clearings, farms, and urban areas. From a distance in space, those changes look like great scars across the surface of the planet. Such land use change modifies the way Earth reflects sunlight. Where there were once dark forests that absorbed much of the light, there are now pale fields or barren ground that reflect more light back into space. This change in reflectivity, called albedo, alters the planet's climate in subtle but real ways, and it is the kind of large-scale environmental modification that a distant observer might notice when studying Earth's patterns. In addition to forests being removed, deserts expand because of human activity combined with natural processes. Overgrazing of land, cutting down too many trees, and overusing water can turn fertile soil into dry sand. These new deserts are not small patches. They spread for hundreds of kilometers, altering the balance of ecosystems and reshaping regional climates. Seen from orbit, the growth of deserts in Africa, Asia, and other regions creates visible changes in the color of the land. Where satellite photos once showed green or brown, newer images reveal increasing patches of pale yellow and white. If another civilization were looking at Earth from light years away, they might detect seasonal and long-term changes in color that are not simply natural but are driven by human expansion and environmental mismanagement. Cities are perhaps the clearest signature of planetary engineering visible from space. At night, urban centers shine with artificial light, but even during the day, their spread leaves permanent marks. Concrete, glass, steel, and asphalt cover what was once soil or vegetation. As cities grow, they fuse into vast metropolitan regions. The eastern coast of the United States, stretching from Boston down to Washington, has become a nearly continuous urban zone. Similar stretches of urban sprawl can be found in parts of Europe, India, and China. From space, these look like enormous grey patches. Unlike forests or rivers, which change with the seasons, cities remain constant. Their straight lines, perfect grids, and spreading circles mark them as something artificial, something that nature alone would not create. One of the strongest signals of planetary engineering comes from agriculture. To feed billions of people, humanity has reshaped land on every continent except Antarctica. Irrigation systems reroute rivers, drain wetlands, and create patchworks of green fields even in dry deserts. When seen from above, regions like the American Midwest or the Nile Delta display neat squares and circles of farmland standing in stark contrast to the irregular patterns of natural landscapes. Crops are planted in strict cycles, and their seasonal changes produce global patterns that can be tracked from space. For an outsider observing Earth, The repeated greening and browning of vast stretches of land at the same time each year might be a clear indicator of deliberate cultivation, not random growth. Water engineering is another way humans have altered the face of the planet. Gigantic dams block rivers, forming artificial lakes so large they can be seen from orbit. The Three Gorges Dam in China created a reservoir stretching more than 600 kilometers, a new body of water that shifted the very rotation of Earth by redistributing mass. Similarly, countless smaller dams and reservoirs around the globe have changed coastlines and river systems, creating geometric shapes visible from above. These projects alter ecosystems and climates downstream. In areas where irrigation canals spread water across deserts, the sudden bloom of green stands out like an engineered signal, very different from the natural flow of vegetation. Climate engineering, sometimes called geoengineering, goes even further. These are deliberate attempts to adjust the planet's atmosphere to counteract warming. Proposals include injecting tiny reflective particles into the stratosphere to bounce sunlight back into space, or seeding clouds to make them reflect more light. If ever put into action on a large scale, such projects would alter the very appearance of Earth's skies. Observers from afar might notice unusual layers of aerosols or cloud patterns inconsistent with a natural climate. Such deliberate climate modification would be one of the clearest examples of planetary engineering, as it is a direct attempt to regulate the environment of the entire world. Glacial retreat and melting ice sheets provide another visible change. For thousands of years, Earth's polar regions have been covered with massive sheets of white ice, which reflect sunlight and keep the climate balanced. In recent centuries, especially the last few decades, those ice sheets have begun to shrink rapidly. Satellite measurements have tracked the shrinking of glaciers in Greenland, Antarctica, and mountain ranges around the world. From space, the reduction in white reflective ice and the increase in dark open water is striking. A distant civilization studying Earth's light might notice a shift toward darker reflection in the polar regions, suggesting some large-scale change in climate. Whether they understood the cause or not, the evidence of a species reshaping its own planet would be clear. Air pollution adds yet another layer of evidence. Factories, vehicles, and power plants release not only carbon dioxide, but also other chemicals like sulfur dioxide, nitrogen oxides, and fine particles. These pollutants form smog and haze that can cover entire regions. In places like northern India or eastern China, the haze can be thick enough to block sunlight for days. Satellites capture images of this smog, showing grey blankets stretching over thousands of square kilometers. Such atmospheric signatures would not be invisible to an alien telescope tuned to the right wavelengths. Certain chemicals, like chlorofluorocarbons, do not occur naturally at all and are purely industrial. If another civilization were to detect them in Earth's atmosphere, it would serve as undeniable proof of technological activity. The ocean also reflects the work of planetary engineering. Humans have overfished certain regions to the point that natural food chains collapse. In addition, large dead zones appear where rivers carry fertilizer runoff into the sea, creating algae blooms that consume all the oxygen in the water. These zones are so widespread that satellites detect changes in water color, as the normally deep blue turns to green or brown with excess algae. Ocean pollution, including billions of tons of plastic waste, alters the reflection of sunlight from the sea surface. On the grand scale, the world's oceans are being reshaped not just by natural currents, but by the cumulative impact of human activity, visible in measurable changes to color, chemistry, and circulation. Dust and smoke from human activities can even travel between continents. Large forest fires, many of which are started by human activity, release so much smoke that satellites track plumes drifting thousands of kilometers. Volcanoes also release smoke, but their plumes follow different chemical patterns and occur irregularly. Human-caused fires follow predictable seasons and regions, and their scale has increased alongside global population. Over time, the steady rise of smoke and dust in the atmosphere is yet another marker that Earth's environment is being engineered, not only on purpose but also through negligence. Mining operations also leave clear marks from space. Gigantic open-pit mines carve deep craters into the surface, creating shapes miles wide. These geometric scars contrast sharply with natural landforms. The extraction of minerals, metals, and fossil fuels leaves behind tailings ponds that shine strange colors under sunlight, often bright red or turquoise. From high above, such features stand out as evidence that someone has been reshaping the ground in search of resources. Large-scale quarrying and strip mining alter entire landscapes, redirecting rivers and leveling hills, changes that accumulate into visible transformations on a planetary scale. Another factor is the spread of infrastructure across the planet. Roads, highways, and railways connect cities and towns, forming networks that are clearly artificial. Highways cut straight lines across mountains and deserts, visible even from orbit. Bridges stretch across bays and straits. Airports form giant geometric patterns, with long runways and clustered buildings standing out from the surrounding land. These networks are the skeleton of a technological species and would not be mistaken for natural formations by a keen observer in space. Artificial reservoirs, coastal expansions, and even whole new islands are more signs of engineering. Countries like the United Arab Emirates and China have built artificial islands that are visible from space, complete with geometric shorelines and even palm tree shapes. These projects change coastlines permanently, adding features that never existed in natural history. For a distant viewer, coastlines are among the most stable features of a planet. To see them altered on short timescales might be a strong hint of intelligent design. Space itself is part of planetary engineering when seen from afar. Thousands of satellites orbit Earth, forming rings of artificial objects around the planet. While tiny compared to Earth, these satellites reflect sunlight, and groups of them, such as communication constellations, can appear as chains of moving points in the sky. To an outside civilization monitoring Earth's environment, the presence of such satellites could serve as a final confirmation that the changes on the surface and atmosphere are not random, but the work of technology. If one were to consider the long-term future, planetary engineering might go even further. Humanity has proposed massive mirrors in orbit to deflect sunlight, giant solar shades to cool the planet, or even the deliberate melting and flooding of certain regions to control sea levels. All of these would leave obvious marks that an observer could not miss. In fact, large orbital structures would block or reflect sunlight in ways detectable even across interstellar distances. Satellite swarms do not form naturally. In nature, you can find groups of rocks circling a planet, such as the many small moons and fragments that circle Saturn or Jupiter, or the dusty rings around Uranus and Neptune. But those rings are random collections of ice and stone. They are messy, spread out, and follow broad and loose patterns. By contrast, a satellite swarm is made of machines designed to follow exact paths, with carefully calculated distances between them, all circling in harmony. This level of order and coordination does not happen by accident. That is why many researchers who study the search for life beyond Earth believe that discovering such a swarm around a distant planet could be one of the most obvious hints that a technological species exists there. One of the clearest examples of this kind of structure on Earth is the growing set of satellites used to provide global internet coverage. Companies have already launched thousands of small satellites into low Earth orbit, and they plan to send up tens of thousands more in the coming years. When seen from the ground, especially just after sunset or before sunrise, they can appear as lines of bright moving dots crossing the sky. Astronomers worry about these swarms because they interfere with telescopes and observations of the stars, but for the purpose of detecting signs of intelligence from far away, they would be very noticeable. If another civilization somewhere in the galaxy had powerful telescopes and they were watching Earth, the constant repeating glints of these machines would be something they could hardly miss. The way these swarms move is very different from the way natural objects behave. A natural ring of debris around a planet does not keep its fragments in straight lines, nor do the objects move in step with one another. Instead, the pieces scatter, collide, and drift apart. But artificial satellites keep to their designed orbits. If you watch them over time, you can see repeating paths, evenly spaced, moving in perfect timing. This repeating structure is an unmistakable sign of planning. The differences between natural rings and artificial swarms are so striking that they might be spotted even by civilizations that are not extremely advanced, but simply patient and careful in their study of the sky. Beyond swarms of satellites, there is another idea that captures the imagination of many thinkers: the building of megastructures in space. A megastructure is something far larger than a single spacecraft or satellite. It could be as large as a whole system of machines working together, or even something that surrounds a planet or star. Some scientists and engineers have speculated about possible structures that a very advanced civilization might build if it had both the knowledge and the energy to do so. These ideas range from massive orbiting power stations to giant solar collectors that could harvest energy directly from a star. While these projects remain dreams for humans today, they are important to consider because they would be easy to detect from far away. An enormous structure in space would change the way light passes around a planet or a star. The shadow it casts or the glint it reflects might give it away. One famous idea is the Dyson sphere, first suggested in the middle of the 20th century. The Dyson sphere is not one single shell, but rather a collection of orbiting pieces that together could capture most of the light of a star. The idea is that a civilization that requires enormous amounts of energy might build such a structure to power its needs. If such a thing existed, astronomers could detect it not by seeing the structure itself, but by noticing the way the star's light was blocked or changed. The star would give off less visible light than expected, but it might shine strongly in the infrared range, since the collected energy would eventually be radiated back out as heat. That unusual signature would stand out from the normal behavior of stars and could point directly to artificial activity. Closer to a planet, megastructures could also include rings of orbiting satellites so numerous and so organized that they form a band that is almost like a man-made ring system. Unlike Saturn's rings, which are wide, diffuse and made of icy fragments, an artificial ring would be composed of machines. Each machine might serve a purpose, such as communication, defense, observation, or power generation. The neatness of their orbits and the uniformity of their size could make such a ring look unnatural. To detect such a system from another star, astronomers might look at the way the planet dims its star's light as it passes in front of it. A natural planet has a smooth and predictable shadow, but a planet with an artificial ring might show strange dips and changes in the light, revealing the presence of artificial structures. There is another important detail to consider: the reflections of sunlight from these machines. Satellites can sometimes shine very brightly when they catch sunlight at the right angle, even brighter than most stars for a short time. This is called a flare. A large swarm of satellites might produce flares so regular and so patterned that they could be spotted even across great distances. The steady glints could look like signals, repeating in ways that nature does not usually create. If a distant civilization built megastructures with reflective surfaces, they could be even easier to detect. A vast mirror or solar collector would shine brilliantly when aligned with a distant telescope. Such signals would be hard to mistake for anything natural. On Earth, we have already created smaller examples of structures that could be considered the beginnings of megastructures. For example, the International Space Station is a large orbiting laboratory where astronauts live and work. Although it is tiny compared to what we think of as a megastructure, it is still a human-made habitat in orbit. Other satellites are equipped with large solar panels that spread out like wings, reflecting sunlight and producing strong flares that can be seen from the ground. As we expand our presence in space, we may one day create larger stations, orbiting cities, or even systems of power-collecting satellites. All of these would contribute to a growing artificial signature that could be seen from other planets. When people think about the future of space industry, they often imagine enormous networks of satellites working together. These networks could mine asteroids, beam energy back to Earth, or create global communication systems. Each of these projects would add to the swarm of artificial objects circling the planet. Unlike natural moons or dust rings, these objects would be evenly spaced, aligned in ways that match mathematical patterns, and they might even change position in coordinated ways. That kind of precision is something that stands out clearly as a product of design, in the same way that archaeologists on Earth can look at an ancient ruin and know it was shaped by human hands rather than by wind or water. Astronomers could look at a well-organized swarm of satellites and know it was the work of technology rather than random chance. The timescale of building such swarms is also important. In just over 60 years since the first satellite was launched in the year 1957, humanity has already filled the sky with thousands of machines. In the decades to come, if current trends continue, there could be tens of thousands or even hundreds of thousands of satellites in orbit. This rapid build-up of artificial objects in such a short time is very different from natural processes, which usually take millions of years. To any observers, this sudden rise in artificial structures would be a strong sign of a young but fast-growing technological civilization. There are also more ambitious ideas. such as building a giant ring around Earth in orbit that could act as a space elevator or transport system. Engineers have proposed orbital rings, which would be vast structures circling the planet strong enough to support vehicles moving into and out of space. If such a project were ever completed, it would be visible from far away, both in the way it reflects light and in the way it changes the pattern of Earth's shadow when it passes in front of the Sun. The clean, circular line of such a ring would look unlike anything formed naturally. The search for signs of life beyond Earth already includes the study of these possibilities. Astronomers are not only listening for radio signals, but also watching for unusual patterns of light and shadow that might be caused by large artificial structures. One example is the unusual star known as Tabby's star, or KIC 8462852, which showed irregular dimming patterns. Some people wondered if this might be caused by megastructures orbiting the star, though most scientists now believe the cause is clouds of dust. Still, the very fact that serious researchers considered megastructures as an explanation shows how real and important this idea has become in the search for intelligence. A swarm of satellites or a megastructure would also have long-lasting effects. While radio signals might fade or be blocked by cosmic noise, a large physical structure can endure for centuries or longer. Even if the civilization that built it were gone, the remains of its orbital systems might still circle its planet. In this way, megastructures could serve as lasting monuments of technology, visible across the galaxy long after the builders themselves had vanished. That permanence makes them especially valuable for the search for signs of intelligence, since they do not depend on constant activity or maintenance to be detectable. There is also the question of scale. A satellite swarm of a few thousand machines is impressive, but it is still small compared to the size of a planet. A true megastructure, on the other hand, could be enormous, spanning tens of thousands or even millions of kilometers. For example, a Dyson swarm around a star would need to be spread out over the entire orbital zone of planets. Such a structure would be visible from across the galaxy. The sheer size of it would leave no doubt that it was the work of intelligence. Even smaller megastructures such as giant orbital habitats or solar collectors would still stand out clearly because of their size and their geometric precision. Some thinkers have also pointed out that advanced civilizations might build structures for purposes we cannot yet imagine. While we think of power collection and communication, they might have other needs or goals that would lead them to construct even stranger shapes in space. These shapes, if large enough, would still be visible to astronomers studying distant planets. A world with massive artificial rings, orbiting cities, or networks of reflective panels would look very different from a natural planet. Its light curves, its shadows, and its infrared output would all tell the tale of technology. The patterns made by artificial objects are perhaps the most important detail. Nature creates beauty, but it does not usually create strict repeating geometry on a cosmic scale. A swarm of satellites arranged in straight lines, evenly spaced, moving in synchrony, would be instantly recognizable as artificial. Megastructures would likely show even sharper lines, smoother surfaces, and repeating angles. These are the hallmarks of engineering. Even if we did not know the purpose of the structure, we would know it was designed. It is also worth thinking about the dangers and challenges that come with such structures. On Earth, we already face the problem of space debris, with thousands of broken satellites and fragments circling the planet. As more swarms are launched, this problem could grow worse, creating hazards for spacecraft and even for life on Earth. For a distant observer, the presence of debris might be harder to detect, but the sheer scale of artificial swarms could still be visible. A civilization that has survived long enough to build megastructures may also have found ways to solve these problems, creating cleaner and more efficient orbital systems. Some of the most fascinating proposals for megastructures go beyond planets and stars. There have been suggestions of building machines on a galactic scale, such as massive lenses to direct light, or giant arrays to send signals across vast distances. While these ideas are far beyond current human ability, they remind us that the concept of artificial orbiting objects does not have to stop at small satellites. The leap from small swarms to enormous constructions may be unimaginable to us today, but to a civilization millions of years older than ours, it might be natural. And if they built such things, they would leave behind clear marks that even we could see with our telescopes. Planets reflect sunlight in predictable ways, based on their surfaces, their clouds, their oceans, and their atmospheric compositions. But when something reflects light in a sharper, more directed or more sudden way, it can look odd. It can create glints, sparkles, or pulses of brightness that raise the question of whether the reflection is natural or artificial. Here on Earth, such reflections happen all the time. Sunlight bounces off oceans, lakes and rivers, creating bright glimmers visible even from space. Ice sheets and snowy mountain ranges shine strongly as well. But beyond these natural sources, artificial structures also create their own glints. Large buildings with glass windows, city skylines, solar panel fields, or even huge antennas can all reflect light in ways different from bare land or water. Satellites orbiting Earth can flash sunlight directly toward observers on the ground, a phenomenon that has been noticed many times. Astronauts in orbit have described sharp flashes from solar panels of other satellites or the International Space Station when the geometry between the Sun, the spacecraft and the viewer lines up perfectly. These sharp glints are different from the broad glow of sunlight bouncing from oceans or deserts. They are narrow, intense, and unmistakably linked to artificial surfaces that are smooth and reflective. If humanity can see such flashes from our own satellites and cities, then perhaps another civilization could notice similar things from far away. When a telescope observes a distant planet, it measures brightness and colour changes as the planet moves around its star. A natural world with oceans might produce a smooth glint as sunlight bounces off the water, much like the bright shimmer we see from Earth's oceans. But if a world had huge cities filled with glass, metal or other reflective materials, the glints might appear sharper and less natural. Artificial satellites circling the planet could also create brief but repeating flashes as they reflected light toward the observer. These patterns could be studied to determine whether the reflections followed natural explanations or suggested something more unusual. Even within our own solar system, observations of unusual reflections have sparked curiosity. For example, spacecraft that orbited Mars and took photographs of its surface sometimes revealed strange bright spots. While most of these turned out to be sunlight reflecting off rocks or ice patches, at first they puzzled scientists. The dwarf planet Ceres, visited by the Dawn spacecraft, displayed bright white patches that looked like glowing lights against its otherwise dark surface. These turned out to be salt deposits reflecting sunlight, but before that explanation was confirmed, people speculated wildly about possible artificial sources. That reaction reveals how sensitive the human mind is to the idea of unnatural glints, and how quickly such observations can spark discussion about advanced beings leaving their marks in space. If we reverse the question, imagining that another civilization is looking at Earth from many light years away, what might they see? Our planet has strong natural reflections from oceans and clouds, but it also has unique artificial reflections. Vast cities shine brightly at night when lights are turned on, though this is not exactly reflection but direct emission of light. During the day, the glass and metal surfaces of cities reflect the sun's rays. A cluster of skyscrapers can create intense flashes, similar to a mirror catching sunlight. Solar power plants, with thousands of mirrors focusing light onto a central tower, generate even stronger directed reflections. Satellites circling Earth, of which there are now thousands, also reflect sunlight. Some of the brightest of these are communication satellites, and those designed for Earth observation, many covered in reflective panels. To an outside observer, Earth might not only look like a planet with oceans and clouds, but also one with glints that do not match purely natural causes. Scientists studying exoplanets have considered ways to detect similar features elsewhere. When light from a star passes through the atmosphere of a planet or reflects off its surface, it carries clues about that world. A smooth ocean reflects in a wide, diffused way, but a flat artificial structure, like a mirror or polished metal surface, would reflect more like a spotlight. This reflection, if aligned properly with Earth's telescopes, could appear as a sharp spike in brightness. Repeated spikes, especially if they appeared at the same orbital positions, would strongly suggest an organized pattern rather than chance. The possibility of artificial satellites creates another layer. Natural moons and rings can reflect light, but their patterns are usually stable and predictable. Artificial satellites, if numerous, could create a cloud of moving reflections around a planet. From far away, this might look like tiny flashes dancing around the world, unlike the stable glow of a natural ring. If a civilization reached a stage where it launched thousands of satellites, as humanity has begun to do, then the signs might be visible to powerful telescopes many light years away. The current effort on Earth to build large networks of satellites for communication has already raised concerns among astronomers because the satellites reflect sunlight and interfere with observations. These reflections, sometimes visible as bright moving streaks in telescope images, are an Earth-based reminder of how orbiting technology leaves clear optical traces. The concept of planetary anomalies extends beyond simple reflections. Imagine a world with large-scale engineering projects, such as giant solar collectors in orbit. These would not only reflect but also block light in unusual patterns. To an outside observer, the planet might show dips and spikes in brightness at odd times, inconsistent with natural clouds or rings. Some scientists have speculated about megastructures, such as vast arrays built to collect a star's energy, which could cause highly unusual light curves when viewed from a distance. Although no confirmed evidence of such structures has been found, a famous case involving a star known as Tabby's star showed strange and irregular dimming that sparked speculation about giant artificial objects. Later explanations pointed more toward clouds of dust, but the case remains an example of how reflections and anomalies can trigger searches for unnatural causes. If we think about the mechanics of reflections, the difference between natural and artificial sources becomes clear. Natural reflections, like those from oceans, are diffuse because waves and surface roughness scatter light in many directions. Snow and ice reflect strongly but across wide angles. Artificial structures, in contrast, tend to have flat, smooth surfaces designed to direct light efficiently. A solar panel or a mirrored window reflects sunlight much like a mirror, sending a concentrated beam in one direction. This is why glints from satellites can be so bright, even though the object is small. The concentration of light makes them stand out against the darker background of space. If similar glints were observed from an exoplanet, scientists would look closely at whether the reflection matched what could be explained by natural features. Some researchers have suggested that searching for these unusual reflections could be a promising way to detect alien technology. Unlike radio signals, which require the civilization to be transmitting at the time, reflections are passive. They happen as long as structures exist and sunlight or starlight strikes them. A planet with reflective cities or orbiting satellites could therefore reveal itself unintentionally. Since telescopes are already improving in their ability to measure light from distant worlds, the search for unnatural glints could become more important in the coming decades. There are challenges, of course. Stars are extremely bright compared to the faint light from their planets, so detecting fine details in planetary reflections is difficult. Clouds and atmospheric changes can also mimic or obscure signals, but scientists are developing ways to separate the light from planets from the overwhelming glare of their stars. Future space telescopes equipped with powerful coronagraphs, which block the star's light, may be able to see planetary surfaces and detect reflective anomalies more clearly. If such technology advances far enough, it might even be possible to see evidence of reflective satellites circling another world. Looking back at Earth again, one can list many specific examples of reflections that might stand out. The salt flats of Bolivia shine so strongly that they can be spotted from orbit. Vast fields of greenhouses in Spain, covered in reflective materials, have been seen from space as bright patches. Airports with long runways, especially when wet, reflect light sharply. Even single large buildings can produce strong glints if their windows align with the sun. Cities full of such buildings create clusters of reflections. At night, while direct reflections are less common, the artificial lights themselves stand out as bright anomalies. Together, these features form a complex mix of signals that make Earth distinct from a purely natural planet. If we ask how long such reflections have been possible, the timeline is revealing. For most of Earth's history, only natural reflections existed. The oceans, ice and deserts reflected sunlight in ordinary ways, but in the last few thousand years humans began to build reflective structures. Ancient temples with polished stone or metal surfaces would have reflected light strongly on small scales. In the last few centuries, with the rise of glass and steel buildings, the effect grew larger. In the 20th century, the launch of satellites added a new layer. Now in the 21st century, with tens of thousands of satellites planned, Earth's artificial reflections are reaching a level where they may be among the most obvious signs of our civilization. One particularly well-known source of satellite reflections was the series of Iridium satellites, launched in the 1990s. These satellites, with large reflective antennas, often produced bright flashes called iridium flares, visible from the ground and sometimes brighter than Venus. People around the world watch these flares, knowing they came from satellites glinting sunlight. If such satellites existed around a distant planet, astronomers might see similar repeating flares, though faint, through powerful telescopes. The presence of reflections can also hint at the materials being used. Natural reflections have characteristic colours. Ice reflects more blue, deserts reflect yellow and red tones, oceans reflect in smooth glints. Artificial materials, especially metals and glass, reflect differently. They might produce sharper glints with unusual colour signatures. Detecting these subtle differences is hard but not impossible. Spectroscopy, the study of light broken into its component colours, allows scientists to look for such details. If a reflection showed spectral features consistent with metal or processed glass, it would be difficult to explain through natural causes alone. Some researchers go further and imagine what advanced civilizations might deliberately build to be seen. For example, a large reflective array in orbit could be used as a signal, producing controlled flashes visible across interstellar distances. By adjusting the pattern, the civilization could send information. On Earth, experiments with heliostats, mirrors that direct sunlight, already demonstrate how large reflections can be controlled. If scaled up, the flashes might be seen light years away. In this sense, reflections are not only accidental signs of activity, but also potential tools for communication. The question of anomalies goes beyond brightness alone. If a planet shows reflections that change in puzzling ways, or at times inconsistent with clouds or seasons, scientists may suspect something artificial. For instance, if glints appear regularly at intervals matching a satellite orbit, that would suggest objects circling the planet. If the glints come from the same surface locations repeatedly, they may correspond to fixed reflective structures like cities. The pattern and timing of these reflections matter as much as their brightness. Natural reflections, though sometimes dazzling, tend to follow predictable rules tied to the planet's geography and climate. Artificial reflections could break those rules. Earth offers countless examples of anomalies that, if seen from afar, might puzzle an alien scientist. The straight lines of highways reflect sunlight differently from irregular natural terrain. Agricultural fields, especially those covered with plastic or irrigation structures, create repetitive reflective patterns. Large solar farms, designed to gather energy, appear as highly reflective patches that could not be mistaken for lakes or ice. Airports, with their long, flat surfaces, would also stand out. To someone studying Earth without context, these reflections might seem very unusual indeed. Beyond Earth, the search for planetary reflections is also tied to the broader hunt for technosignatures, or signs of technology. While most efforts have focused on radio signals, optical technosignatures like reflections are becoming more important. Unlike signals that require active transmission, reflective anomalies simply exist, and they might persist for centuries even if the civilization itself has changed. This durability makes them appealing targets for search strategies. As telescopes improve, scientists will be able to look at more planets in greater detail. Already, researchers are beginning to analyze the glint of oceans on exoplanets as a way to confirm the presence of water. If oceans can be detected, then artificial glints might also be found. The difference between the two lies in sharpness and regularity. Oceans produce broad, smooth glints that shift gradually as the planet rotates. Artificial structures produce sudden, narrow glints that repeat precisely. Detecting these would require careful measurements over time, but the potential payoff is enormous. The human imagination naturally gravitates to the idea of spotting a reflection from an alien city or spacecraft. When people first started to think about life beyond Earth in a serious and scientific way, the idea of sending signals to other worlds became one of the earliest approaches. The Earth is a small planet in a large galaxy, and if life developed here, then perhaps it also developed somewhere else far away. But to reach across the huge distances between stars, light itself seemed too slow in terms of travel, while physical journeys with ships were beyond reach for many thousands of years. Radio waves, however, were something different. They moved at the speed of light, travelled across space with far less energy loss than sound or physical movement, and could be focused into beams aimed directly at distant stars. This idea gave rise to something unique: intentional radio beacons, built and transmitted with the hope that one day a civilization far from us might intercept them. The very beginning of this way of thinking can be traced back more than a century ago, when the technology of radio was still young. Guglielmo Marconi, one of the earliest pioneers of radio communication, speculated at the start of the 20th century that perhaps signals could be sent across interplanetary distances. He was not alone in his thought. Nikola Tesla, around the same period, also suggested that powerful radio transmitters might even reach Mars. These early dreams were not based on accurate understanding of how vast the distances really were, but they introduced the idea that radio could connect Earth to the wider universe. While neither Tesla's nor Marconi's attempts succeeded in actually contacting other worlds, they laid the groundwork for later scientific programs that would approach the problem with more precision. By the middle of the 20th century, radio astronomy had developed into a serious science. Large parabolic dishes were being constructed to collect faint signals from stars, galaxies, and nebulae. In the year 1959, two scientists, Giuseppe Cocconi and Philip Morrison, published a paper in the prestigious journal Nature, in which they argued that searching for extraterrestrial civilizations should focus on the radio spectrum, especially near the frequency of 1420 MHz, the natural emission line of neutral hydrogen. They reasoned that hydrogen is the most abundant element in the universe, and a civilization with radio technology would surely know this frequency. This paper directly inspired later efforts such as SETI, the search for extraterrestrial intelligence, and it also raised the question of not just listening, but sending out a signal that others could hear. One of the most famous examples of such an intentional beacon was created in the year 1974. At the Arecibo Observatory in Puerto Rico, a massive radio dish stretching more than 300 meters in diameter was used to send a carefully crafted message into space. The occasion was a ceremony marking the upgrade of the observatory's equipment, and the director at the time, Frank Drake, who was already a pioneer of SETI, worked with Carl Sagan and other scientists to design the content. The message was transmitted with a power of 1,000 kilowatts, aimed at the globular star cluster Messier 13, located about 25,000 light-years from Earth. Although no one expected the message to actually be received in the near future, since it would take 25,000 years just to arrive, it was a symbolic act to demonstrate both human capacity and intent. The Arecibo message was not written in words, but instead in a pattern of binary digits, zeros and ones, which could be arranged in a rectangle of 73 rows and 23 columns. These numbers were chosen because they are prime numbers, and a receiving intelligence might notice that and attempt to reconstruct the message in its correct form. Once arranged properly, the message formed a set of pictorial representations. Numbers from 1 to 10, the atomic numbers of elements important for life such as hydrogen, carbon, nitrogen, oxygen, and phosphorus. The formulas of basic nucleotides that make up DNA, a sketch of the double helix structure of DNA, a small figure of a human with his height indicated, the population of Earth at that time, a drawing of the solar system with Earth highlighted, and finally a schematic of the Arecibo telescope itself. In just 1,769 bits, the designers tried to present both a self-portrait of humanity and a hint of the technology used to send the signal. While the Arecibo message was the most publicized, it was not the only intentional beacon that has ever been created. Before it, in the early 1960s, Soviet scientists also attempted transmissions aimed at nearby stars. One of the earliest was from the Evpatoria planetary radar in Crimea, which sent coded signals in the direction of Venus and Mars for scientific radar studies, and later toward other stars in an effort to reach beyond the solar system. These experiments were small and mostly experimental, but they demonstrated the willingness of human beings to shout into the cosmic void with technology as soon as they had it. In the following decades, more projects followed. In the 1990s, the Evpatoria facility again became the center of such transmissions. In 1999 and 2003, a project known as Cosmic Call was organized by a group of scientists and enthusiasts. They used the powerful 70-meter antenna at Evpatoria to transmit digital messages toward a series of nearby sun-like stars. These messages included mathematical content, scientific information, and also cultural material submitted by people around the world. The idea was to give not just the raw facts of science, but also something about humanity's diversity and creativity. The messages were carefully coded into binary so that they could, at least in theory, be reconstructed by a distant intelligence that might not share any of our languages or symbols. Another related effort was the Teenage message sent in 2001 also from Evpatoria. This project was unusual because it included a musical interstellar radio transmission, created by Russian teenagers using a theremin, an electronic musical instrument. The broadcast consisted of greeting messages, cultural information, and melodies. In this way, the attempt was both scientific and artistic, blending the technical power of radio with the human desire to communicate feelings and creativity, not just raw data. These efforts raised deep questions about whether sending messages is wise or reckless. Some scientists, such as Stephen Hawking, warned against active signaling, suggesting that any civilization advanced enough to intercept such signals might not have friendly intentions. Others argued that the danger is minimal since Earth has already been unintentionally leaking radio and television signals for more than a century, and anyone close enough to hear would already know of our presence. Supporters of intentional beacons believe that taking the step to send directed, strong, and clear messages is a way to demonstrate maturity as a species, showing that humanity is willing to reach out to the unknown with openness. In 2008, a project called A Message from Earth sent a digital time capsule toward the star system Gliese 581, which was known to host several exoplanets, including some considered potentially habitable. The message was composed of over 500 text, picture, and audio contributions gathered through an internet campaign. The transmission was made from the RT-70 radar telescope in Ukraine. Since Gliese 581 is about 20 light-years away, the message will arrive in a few decades, which, compared to the Arecibo message, is a relatively short waiting time. Though no one truly expects a reply, the fact that the signal is aimed at a system of real, potentially life-bearing planets makes it symbolically powerful. Throughout all of these attempts, the technical side of building a radio beacon has been carefully considered. To be detectable across interstellar distances, the signal must be both strong and distinct from natural sources of radio emission. Stars, pulsars, and other cosmic objects produce a wide variety of radio noise. A message must stand out by being narrow in frequency, highly regular, or by containing unmistakable mathematical patterns. For example, a simple beacon might be nothing more than a series of pulses timed according to prime numbers. Such a pattern is unlikely to be produced by any natural process, and would therefore indicate artificial origin. More elaborate messages can then be encoded, but the first step is always to get attention with something undeniably artificial. Another challenge is that radio waves spread out over distance. Even a powerful transmission, when spread over many light years, becomes faint. A targeted, narrow beam transmission is more efficient than broadcasting in all directions. The Arecibo dish, for example, was able to concentrate its signal into a beam just a few arc-minutes wide. This makes the signal much stronger at the chosen target, but also means that it misses everything else. To reach many stars, many transmissions would be required, or the beam would have to be moved systematically over time. This introduces the problem of resources, since such broadcasts require significant amounts of energy and telescope time. There have been proposals to create dedicated interstellar beacons that would broadcast continuously for decades or centuries. One idea, promoted by scientists like Alexander Zaitsev, was to construct a transmitter that would operate like a lighthouse, sweeping across the galaxy with a repeating signal. The energy costs would be high, but it could guarantee that any nearby civilization with the ability to listen would eventually notice. However, such large projects have never been realized, partly because of cost, partly because of political hesitation, and partly because the scientific community has not reached agreement on whether sending such messages is a good idea. When thinking about these intentional radio beacons, it is important to note that humanity has also sent physical messages aboard spacecraft. The Pioneer plaques on the Pioneer 10 and 11 spacecraft in the early 1970s and the Voyager Golden Records launched in 1977 were examples of such attempts. These were not radio beacons, but physical artifacts carrying information into interstellar space. The difference is that they travel slowly, taking hundreds of thousands or millions of years to reach the nearest stars, whereas radio messages move at the speed of light. Both methods reflect the same basic human impulse, the desire to communicate beyond Earth. Over time, advances in digital technology have changed how messages are designed. In the early days, simple binary codes and pictorial representations were used, since it was assumed that mathematics and science are universal languages. More recent attempts have included compressed digital files containing images, sounds, and even video, on the assumption that an advanced civilization might be able to decode such formats. Some projects have even experimented with transmitting structured data that could, in principle, reconstruct a simple software program or a set of instructions for building a computer capable of displaying the message content. These ideas show how the concept of interstellar communication continues to evolve as human technology does. One interesting aspect of these projects is the involvement of the general public. Whereas the Arecibo message was designed by a small group of scientists, later efforts such as Cosmic Call and A Message from Earth invited people from all over the world to contribute. This reflects a shift from viewing interstellar messages as purely scientific demonstrations to seeing them as cultural and collective acts, representing humanity as a whole rather than just its technical experts. The inclusion of art, music, personal greetings, and cultural symbols reflects the belief that if we are ever heard, we should not just send cold data, but also something that conveys what it is like to be human. The debate over whether to continue building such beacons remains unresolved. Some say that Earth should remain quiet until we know more about what kind of civilizations may exist. Others argue that silence is pointless, since we already stand out to anyone advanced enough to look. Supporters of active messaging point out that if every civilization chooses only to listen and never to send, then the galaxy will remain silent forever. To break this silence, someone must take the first step. Whether or not our attempts succeed, they establish a record of human beings as a species willing to reach beyond itself. Today, the search for extraterrestrial intelligence continues mostly in listening mode, with large radio telescopes scanning the sky for unusual signals. But the legacy of intentional radio beacons remains important, both as technical experiments and as symbolic gestures. The Arecibo Observatory itself, though it collapsed in 2020, remains remembered in part for that single, dramatic transmission in 1974. Other projects continue sporadically, sometimes organized by universities, sometimes by private groups, sometimes by collaborations between space agencies and cultural organizations. Each attempt adds another layer to the history of humanity's effort to reach out. Looking into the future, the possibility of building more powerful and longer-lasting beacons is closely tied to our growing abilities in energy generation and space infrastructure. A civilization with large-scale solar power satellites, or even megastructures in space could, in theory, create transmitters far more powerful than anything we have today. If such projects are ever built for our own use, they could also serve as instruments for sending messages. Some scientists have even proposed using tightly focused laser beams rather than radio, as lasers can carry large amounts of information and may be more efficient over long distances. Experiments have already demonstrated the ability to send laser pulses across the solar system to spacecraft. Extending this idea to interstellar scales is a logical next step. The concept of intentional radio beacons also shapes how we think about finding others. If we assume that another civilization might have done something similar, then SETI researchers can look not only for accidental leakage, but for deliberate, strong, patterned transmissions. This guides the choice of frequencies, signal types, and strategies used in the search. In this sense, by building and sending our own beacons, we also train ourselves to recognize what others might do. Each message is both an attempt at contact and a practice in imagining what a real detection might look like. In the late 1970s, when people on Earth were still learning how to send spacecraft far into the solar system, a decision was made that went beyond ordinary science and engineering. Two spacecraft, named Voyager 1 and Voyager 2, were being prepared to travel past the outer planets and then continue into the deep unknown of interstellar space. Those spacecraft were launched in the year 1977, during a period when new technology was rapidly changing human life. Yet at the same time, there was a deep sense that humanity was only beginning to take its first steps beyond its homeworld. To give these spacecraft a special purpose beyond just gathering scientific data, a unique idea was proposed. If these machines would leave the solar system and wander between the stars for perhaps billions of years, why not attach to them a kind of message, a small time capsule, something that could speak on behalf of Earth and the beings who live on it? From that idea was born the Voyager Golden Record. The Golden Record was not simply an object of art, nor just a scientific sample. It was both practical and symbolic, a kind of bottle tossed into the vast ocean of space, carrying within it the essence of Earth. The record was designed as a phonograph disc made of copper and coated with gold. The The gold was chosen not just for its beautiful appearance, but also because it is a metal that resists corrosion, and in the cold emptiness of space, where there is no air or water to wear it down, it could last for perhaps more than 1 billion years. If someday far away in time and distance another intelligent civilization were to encounter one of the Voyager probes, they might pick up this disk and find a way to play it, discovering the message stored inside. The record contained both sounds and images, carefully selected by a team of scientists, artists and thinkers led by the astronomer Carl Sagan. They faced a difficult but exciting challenge. If you had to describe all of humanity and the planet Earth to complete strangers who may not look like us, may not think like us, and may not even sense the world in the same way we do, what would you choose? Only a limited number of sounds and images could be stored, so the choices had to be powerful, meaningful, and as universal as possible. The team wanted to show both the diversity and the unity of life on Earth. They wanted to include not just scientific facts, but also feelings, culture, art, and music. The record therefore became a collection of greetings in many languages, natural sounds from the Earth, musical pieces from across the globe, and a library of images that told the story of the planet and the people living on it. The sounds on the record included greetings in 55 different human languages, from ancient dialects to modern tongues. A child's voice in English said, "Hello from the children of planet Earth," carrying the innocence and hope of younger generations. There were greetings in languages such as Sumerian, which was already long extinct, as well as Chinese, Arabic, Spanish, Hindi, and dozens of others spoken by millions of people. Each greeting was simple and short, usually just a phrase of welcome, but together they formed a chorus of voices that stretched across human history and culture. The idea was not to teach another species how to speak our languages, but to demonstrate that Earth is home to many peoples, many ways of speaking, and many forms of thought. Alongside the human voices were the sounds of the planet itself. The record carried the sound of wind, rain, ocean waves, and the rumbling of thunder. It included the songs of birds, the calls of whales, the barking of dogs, and the footsteps of humans. There were recordings of tools being used, a blacksmith hammering, and even the sound of a rocket launching marking humanity's reach for the stars. These sounds were meant to express that Earth is a living world, full of both natural forces and technological activity. To an alien listener, such sounds might be mysterious, but they would also be unmistakably the signature of a planet rich in life and creativity. One of the most remarkable parts of the Golden Record was its music collection. Carl Sagan and his team decided that music could be a universal form of communication, since even if another civilization could not understand our languages, they might still perceive rhythm, melody, and harmony. The record included classical works such as Bach's Brandenburg Concerto and Beethoven's Fifth Symphony. It also carried traditional songs from around the world, a Navajo night chant, Peruvian panpipes, Australian Aboriginal music, and wedding songs from Bulgaria. It included blues from the American South, Indian reggae music, and even a recording of Chuck Berry's rock and roll hit Johnny B. Good. The inclusion of that lively modern song sparked debate, with some critics wondering if rock and roll was an appropriate message to the stars, but Carl Sagan argued that it showed the diversity of human expression and the vitality of popular culture. By mixing the ancient with the modern, the sacred with the playful, the record painted a broad picture of what human beings create when they make music. The record also carried more than 100 images encoded in analog form. These images were not stored as digital files, since this was long before the internet age, but instead they were converted into patterns of light and dark that could be reconstructed if someone learned how to play the record correctly. The images began with scientific diagrams such as mathematical definitions, the structure of DNA, and the location of our solar system. Then came pictures of the planets, landscapes of Earth, and scenes of human life. There were photographs of mountains, rivers, animals, forests, and people from different cultures. One picture showed a mother and child, another showed athletes running, others depicted architecture, agriculture, and technology. The images were chosen to be simple enough to understand, but also rich enough to convey the complexity of Earth. To any finder, they would be like windows into the everyday existence of a distant civilization. An especially thoughtful detail was the inclusion of a pulsar map, engraved onto the cover of the record. This map used the positions and frequencies of 14 different pulsars to show exactly where our solar system is located in the galaxy. Pulsars are rapidly rotating neutron stars that emit precise beams of radiation, like cosmic lighthouses. Because each pulsar has a unique rotation period, they act almost like fingerprints in space. By showing their patterns, the map could allow a finder to trace back to Earth's position, even if millions of years had passed. In addition, the cover also showed a diagram explaining how to play the record, including the speed of rotation and how to decode the images. The instructions were written not in words but in scientific symbols, in the hope that mathematics and physics would be universal languages that any advanced civilization could understand. The making of the Golden Record was done in a very short time, only a few months, since the Voyager spacecraft were already close to their launch dates. Carl Sagan's team worked long hours debating what to include. They had to balance the scientific desire for accuracy with the poetic desire for beauty. They also had to keep in mind the physical limits of the record, since only a few hours of sound and a little over 100 images could be stored. Despite these limits, they managed to create something extraordinary, a small but powerful portrait of an entire planet. The launch of Voyager 2 took place first, on August 20th of 1977, followed by Voyager 1 on September 5th of the same year. Each carried its own golden record mounted on the spacecraft, protected by an aluminum cover and accompanied by a cartridge and needle, ready to be used if ever discovered. As the spacecraft travelled past Jupiter, Saturn, Uranus and Neptune, they sent back images and data that transformed human knowledge of the outer planets. But after their planetary missions were complete, the spacecraft continued outward, carrying with them their golden cargo. Voyager 1 is now the farthest human-made object from Earth. It crossed into interstellar space in the year 2012, travelling beyond the influence of the Sun's solar wind. Voyager 2 followed into interstellar space in the year 2018. Both spacecraft are expected to keep moving for billions of years, long after their power supplies have failed, and long after all human beings alive today are gone. In that distant future, the golden records will still be intact, slowly drifting among the stars waiting to be found. The meaning of the golden record goes beyond the possibility of it being discovered. It is also a statement about humanity itself. It reflects the desire to reach out, to communicate, to declare that we exist and that we have something worth sharing. At a time when the Cold War still divided nations, the golden record was a gesture of unity, presenting Earth not as separate countries but as one world. It was also a gesture of hope, expressing the belief that communication across the cosmos is possible, even if the chances are small. The record may never be found, but the act of creating it was itself a powerful symbol of imagination and aspiration. Many people who have studied the golden record feel that its most touching elements are the small, personal touches. For example, Carl Sagan included a recording of his wife Ann Druyan's brainwaves. She had been asked to think of many things during the recording: the history of Earth, the future of humanity, and her love for Carl, to whom she had just become engaged. In those brainwave patterns, preserved in the record, are not only scientific data, but also deep human emotion. There is also the laughter of children, reminding anyone who hears it of innocence and joy. These details make the record more than a scientific archive. They make it a living expression of humanity's heart. The golden record has inspired artists, musicians and writers for decades. It has been referenced in novels, songs and films. It sparks questions about what messages we might send if we were to create a new record today. Would we include digital video, internet archives, or modern music? Would we choose different greetings, knowing how much the world has changed since 1977? Or would we keep the record just as it is, a time capsule of that particular moment in human history? The record remains a reminder that Earth is capable of thinking on a cosmic scale, of imagining itself in relation to the stars. The very act of sending a message to unknown beings requires imagination and humility. The makers of the record knew that the chances of it being found were extremely small. Space is vast, and the Voyagers are tiny compared to the galaxy. Yet they believed that even a small chance was worth taking. Just as people on Earth send letters in bottles into the sea, knowing they may never be discovered, so too did humanity send this message into the cosmic ocean. The golden record is therefore both a scientific artifact and a work of hope, combining knowledge, art and human spirit into one golden disc. When we think of the record travelling silently among the stars, we might reflect on how fragile and precious Earth is. All the voices, All the sounds, all the music, all the images, they come from one small blue planet orbiting one ordinary star. The golden record is like a mirror in which we see ourselves not divided by nations or languages, but united as one species on one world. It captures a moment when humanity decided to speak not just to itself, but to the universe. And so the golden record remains, riding aboard the Voyagers through endless night, carrying greetings from Earth, carrying the laughter of children, the heartbeat of lovers, the roar of thunder, the music of Bach and Chuck Berry, the images of mountains and rivers, the patterns of DNA, and the coordinates of our solar system. It will continue its journey long after every library on Earth has crumbled, long after mountains have eroded, long after the continents have shifted. In the cold silence between the stars it will drift, a golden echo of Earth, a time capsule of sounds and images, waiting across the ages. For many centuries, people only dreamed of another intelligent being, but in more recent times, science and technology have made it possible to actually try reaching beyond Earth with signals that could carry information. The practice of deliberately sending out messages to unknown civilizations is often called Meeti, which stands for Messaging to Extraterrestrial Intelligence. It is different from listening passively, because instead of only waiting for signals, people are now choosing to speak first, using powerful radio transmitters, carefully designed codes, or even beams of light. These modern projects are international in nature because they involve scientists, engineers, writers, musicians, linguists, and philosophers from many different countries who come together with the same goal: to create a message that might survive across the distances of space and time, and perhaps someday reach ears or minds that are not human. Unlike accidental signals that leak into space when we broadcast television shows, radio transmissions, or military radar, these deliberate attempts are carefully built to maximize their chances of being noticed and understood. Scientists have debated for decades whether it is wise to shout into the dark, because there is always the question of who might be listening. Yet curiosity and imagination have pushed people to go forward. Meeti projects combine science with art and human culture, because they are not only technical exercises, but also creative expressions of what it means to be alive on Earth. To send a message on behalf of all humanity is not a small thing. It requires deciding what to include, what language or symbols to use, and how to compress the vast richness of human experience into a single message that might last millions of years. One of the most well-known early examples that inspired modern Meeti work was the Arecibo message, sent in the year 1974 from the Great Radio Telescope in Puerto Rico. That message was a short sequence of binary digits, only 1,679 bits long, which when arranged in a grid showed pictures of a human being, our solar system, DNA structure, and the numbers 1 through 10. But that transmission was more of a symbolic gesture during a ceremony than a serious attempt to communicate. It was beamed toward a distant star cluster that would not be in range for tens of thousands of years. Still, the Arecibo signal became a seed in the imagination of many researchers who would later form Meeti International and other organizations dedicated to modern projects. In the 21st century, these projects became more organized and intentional. A group of scientists, artists, and cultural thinkers created Meeti International to advance the effort of sending new interstellar messages. They held conferences to discuss not only the technical details of transmitting, but also the ethics of representing Earth. Should humanity try to say hello? Should we describe our biology in detail, or keep things simple? Should we include music, art, or even mathematical puzzles? The decisions reveal what we value and how we imagine another mind might try to understand us. This international character is very important because no one country owns the right to speak for all of Earth. When Meeti International develops a project, it invites voices from many backgrounds so that the message does not carry only one culture's perspective, but a shared picture of humanity. One of their modern projects took place in the year 2017, when a series of carefully crafted signals were sent toward a nearby star system called GJ273, also known as Luyten's star, which lies about 12 light-years away. The message was beamed from a radio telescope in Tromsø, Norway, and it included musical compositions as well as mathematical tutorials. The plan was to create a package that could be understood even by beings with no prior knowledge of Earth, starting with simple pulses that established a counting system and moving gradually to more complex structures. At the same time, the inclusion of music allowed for a more emotional and artistic representation of humanity. Music does not require words. It is made of patterns of sound and rhythm that could be recognized as intentional and meaningful by any creature able to hear or sense vibrations. The idea was that even if an extraterrestrial intelligence could not fully decode our mathematics, they might still notice the emotional shape of music. This project attracted attention because it was not just scientists speaking, but artists too. Composers from different countries contributed pieces that were transmitted as digital sound. Each piece became a kind of ambassador for human creativity. The transmission itself was not extremely powerful compared to the largest radars on Earth, but because Luyten's star is relatively close by cosmic standards, the message might have a chance of being detected. If a civilization exists there and has the technology to receive faint radio signals, they might notice that a small planet around another star is calling out. The round-trip time is daunting, though. A signal travelling at the speed of light will take 12 years to reach Luyten's star, and if anyone responds, their reply would take another 12 years to return. That means the earliest possible answer could arrive in the year 2041, and only if someone is indeed listening. The GJ273 project was not the only attempt. Meeti International has also worked with cultural institutions to hold public workshops and festivals where ordinary people can help design parts of a message. This democratic approach allows children, artists and communities to imagine what they would want to say if they had the chance to introduce Earth to the cosmos. In one such effort, people were asked to write short texts or draw symbols that represent peace, curiosity or everyday life. These contributions might not be transmitted directly yet, but they help build a library of human expression for future signals. By involving the public, Meeti International turns the act of communication into a shared human project rather than something hidden in laboratories. Another major component of these modern projects is the debate about safety. Some researchers, including famous figures such as Stephen Hawking before his passing, in the year 2018, warned that advertising our presence could be risky. They imagined scenarios where a more advanced civilization might treat Earth the way European colonizers once treated distant lands they discovered, sometimes with conquest rather than friendship. Others argued that the universe is vast, and the likelihood of hostile invaders finding and reaching us is very small compared to the value of trying to connect. Meeti International has addressed these concerns by holding open discussions, publishing their plans, and inviting criticism, because they believe any attempt to speak for Earth must be transparent. This openness itself becomes part of the project, showing that humanity is not only technologically capable, but also socially aware of the consequences of its actions. Modern attempts also use more sophisticated technology than in the past. Whereas the Arecibo telescope was a single giant dish, today arrays of antennas and more sensitive instruments allow for higher resolution transmissions. Digital encoding methods can embed layers of information, from simple pulses to complex images or sounds, all within the same signal. Scientists design these signals with redundancy, so that if parts are lost in space noise, the overall message can still be reconstructed. Some projects experiment with frequency choices. For example, the so-called waterhole region of the radio spectrum between 1420 MHz and 1660 MHz is thought to be a natural band where civilizations might choose to communicate, because it is relatively quiet and corresponds to emissions of hydrogen and hydroxyl, the components of water. By transmitting in this band, Meeti signals might be easier to distinguish as artificial. There are also experiments with using lasers as beacons. Short pulses of laser light can travel far through space and might be easier to notice against the dark sky than radio waves, depending on the observer. Some proposals involve sending periodic laser flashes toward nearby stars, encoded with patterns that could represent numbers or images. While this method requires extremely precise targeting, it shows how Meeti projects explore many possible channels to maximize the chance of being seen. In all of these methods, the guiding principle is deliberateness. A natural source might make noise, but a deliberate pattern of mathematics, repeated sequences, or musical rhythms stands out as something made by intelligence. In recent years, Meeti International has partnered with other organizations to expand beyond pure science and incorporate elements of philosophy and art. They host conferences called Language in the Cosmos, where linguists, semioticians, and communication experts discuss how meaning is created. If an alien species has senses completely different from ours, how could they interpret signals? What kinds of universals exist that might bridge the gap? Numbers, for example, might be universal because they describe relationships between quantities that do not depend on culture. Likewise, physical constants such as the speed of light or the structure of atoms are likely to be recognized by any scientific mind. These could form the foundation of a common language. From there, one could build up more complex expressions, such as diagrams of molecules, drawings of living beings, or eventually music and human speech. The creation of a message often resembles building a ladder. At the bottom are simple pulses, then patterns, then numerical sequences, then depictions of geometry, then representations of biology and culture. Each step assumes the receiver has managed to decode the previous one. In this way, a message is not just data but a lesson plan, teaching the basics before revealing more. Meeti International emphasizes this ladder approach because it mirrors how we teach children or newcomers to a subject. Start with what is most universal, then move toward the specific and unique. Some Meeti projects have even experimented with sending representations of human languages. For instance, short samples of spoken greetings in many tongues have been encoded digitally, not because we expect aliens to understand them immediately, but because they show the diversity of human voices. When the Voyager spacecraft were launched in the year 1977, they carried the famous golden records with greetings in 55 languages. That idea continues to inspire Meeti efforts, showing that words and sounds can carry emotional weight even if the precise meaning is lost. The tone of a human voice saying hello may communicate friendliness without translation. Modern transmissions can extend this by including not only speech, but also videos, music, and art, compressed into radio signals that could be reassembled by a curious receiver. There is also the challenge of longevity. A message sent today might take hundreds or thousands of years to be noticed, depending on where it travels. By then, human societies may have changed drastically. What if the beings who receive our signal long after we're gone believe that it represents all of humanity forever? To address this, Meeti International often designs messages that are less about current politics or trends and more about fundamental aspects of life. The structure of DNA, the arrangement of our solar system, mathematical logic, the sounds of nature, and the emotions expressed through music and art. These are more timeless than news events or fleeting cultural fashions. In this way, the message becomes a kind of time capsule, representing humanity in a way that could still make sense thousands of years later. The excitement of these projects lies not only in the slim chance of being answered, but also in what they do for us on Earth. When people gather to decide what to say to another world, they are forced to think about what matters most. Are we defined by our science, our art, our kindness, or our struggles? How do we compress the vastness of human history into a signal only a few minutes or hours long? These questions encourage reflection about identity and purpose. They bring together disciplines that rarely meet: astrophysics with poetry, computer science with painting, linguistics with philosophy. Meeti International functions as a bridge, reminding people that communication is not just technical, but also deeply human. In the coming decades, more projects are likely to emerge. Advances in telescope technology will provide stronger transmitters and more precise aiming. International collaborations may develop protocols for how to craft messages responsibly, involving global participation rather than isolated groups. There may even be discussions at the United Nations about who has the authority to approve interstellar messages. Already some have suggested that a democratic process should decide, perhaps through worldwide polls or representative committees. Because once a message is sent, it cannot be taken back. It will travel at the speed of light forever, carrying a snapshot of Earth across the stars. This awareness adds weight to each attempt. Sending out a Meeti signal is like placing a bottle in an infinite ocean, with no guarantee it will ever be found. Yet the act itself is meaningful. For many involved, the purpose is not only to reach aliens, but to unite humanity in a shared dream. The sky becomes less of a cold emptiness, and more of a stage where Earth can perform its first introduction to the cosmos. Whether or not someone hears, we have spoken. That act transforms how we see ourselves. If in some distant future, perhaps centuries from now, a reply is received, it could be the most extraordinary moment in human history. But even if no reply ever comes, the process of creating these messages enriches us. The music, art, mathematics, and philosophy woven into Meeti signals are gifts that we first give to ourselves before casting them outward. In that sense, Modern deliberate attempts to communicate are as much about humanity learning to speak with one voice as they are about contacting others. The pioneer plaques were among the earliest physical attempts by humankind to reach across the vastness of space, with a message intended not for ourselves, but for whoever might someday find them. They were not electronic signals that would fade, nor radio waves that would vanish into the background of the universe, but actual solid engravings carried aboard spacecraft launched into the great unknown. These plaques, small in size yet enormous in meaning, represented a deliberate gesture to tell any being that might come across them who we are, where we come from, and what kind of creatures inhabit the pale blue planet circling an ordinary star. The idea behind them was both simple and bold. If a spacecraft is already leaving the solar system, why not attach a greeting, a universal calling card, carved into metal that might last longer than any human monument on Earth? In the early 1970s, when the United States was sending the Pioneer spacecraft to explore Jupiter and beyond, a man named Carl Sagan, who was both a scientist and a dreamer, along with his colleagues Frank Drake and Linda Salzman Sagan, decided that these spacecraft could carry something more than instruments and cameras. They could carry a message that outlived the machines themselves. They designed a plaque that would not only withstand time, radiation, and cosmic dust, but also might be readable to an intelligent mind, no matter how different from our own. The material chosen was anodized aluminum, mounted on the spacecraft in such a way that it would be shielded from erosion. It was small, about 9 by 6 inches, yet on this limited space they tried to summarize the essence of our existence. The design of the plaque was a mixture of scientific precision and poetic imagination. At its heart were figures of a man and a woman, drawn in clean outlines. They stood side by side, with the man raising his hand in a gesture that might be seen as a greeting. The woman stood with her arms at her sides, her posture calm. Both figures were drawn naked, because clothing would only confuse an alien species that would not know what garments meant. Their bodies were meant to display the basic form of human beings, though they were sketched in a simple schematic style, not in detailed realism. Behind them was drawn the outline of the spacecraft itself, to give a sense of human scale. This was crucial, because otherwise the figures could be misinterpreted as giants or tiny creatures. By including the spacecraft, the designers hoped to show the relative size of human beings compared to the machines we build. Next to the figures, at the top left of the plaque, was a burst of lines radiating outward from a single point. This was the most scientific part of the message, a kind of galactic map. It depicted the position of our Sun relative to 14 pulsars, which are rapidly rotating neutron stars that emit precise radio pulses. Each line pointed toward a pulsar, and alongside each line were markings indicating the frequency of the pulsar's signal, written in binary notation. Because pulsars slow down predictably over millions of years, any intelligent being that found the plaque could, in theory, use this map to locate our Sun in both space and time. It was like giving cosmic coordinates, drawn not with words but with universal physics. Beneath the pulsar map was a simple drawing of our solar system. The Sun was shown with the planets arranged in order, from Mercury to Pluto, which at the time was still counted among the planets. A small arrow pointed from the third planet, Earth, toward the spacecraft itself, showing where the journey had begun. This small arrow was a humble attempt to point homeward, a cosmic signpost saying, "We came from here." The design was deliberately simple, relying on basic shapes and proportions that, it was hoped, could be understood by beings who might not share our languages or symbols. Another important part of the plaque was the diagram of a hydrogen atom, the simplest and most abundant element in the universe. The plaque showed the transition between the two lowest states of hydrogen, represented by 2 small circles and a line. This was not chosen at random, but because hydrogen is universal, and the transition produces radiation at a wavelength of 21 centimeters, which is a fundamental physical constant. The designers hoped that any advanced civilization capable of interstellar travel would recognize this depiction. This transition served as a kind of Rosetta Stone for the rest of the information, giving a unit of measurement for both time and distance. Once the hydrogen transition was understood, the rest of the plaque's symbols could be scaled accordingly. Though the plaque contained only a handful of elements, together they formed a message that reached far beyond their simple engravings. It was a combination of human form, universal science, and cosmic cartography. The figures said, "This is what we look like." The solar system diagram said, "This is where we are." The pulsar map said, "This is how to find us." The hydrogen atom said, "This is how to read the units." In just a small rectangle of metal, humankind attempted to condense both identity and address, existence and invitation. The plaques were mounted on Pioneer 10 and Pioneer 11, spacecraft launched in the year 1972 and 1973. Pioneer 10 was launched first, in March of 1972, and it became the first human-made object to travel through the asteroid belt and make a direct encounter with Jupiter. Pioneer 11 followed in April of 1973, and it went on to fly past Jupiter and Saturn, sending back images and data never before seen. Both spacecraft were launched with the understanding that, after completing their missions within the solar system, they would continue on trajectories that would carry them outward into interstellar space. They would become silent travelers, drifting among the stars, their instruments long dead, but their plaques still intact, carrying the engraved message. At the time, these spacecraft were marvels of engineering, but it was also understood that their functional lifespans would be short compared to the billions of years they might wander the galaxy. Within a few decades, their transmitters would fall silent, but the plaques, bolted to the frames of the spacecraft, would endure. They would not corrode in the vacuum of space. They would not decay quickly. Even millions of years from now, should they encounter another star system, the etchings might still be legible. This was part of their beauty. They were designed not for the short attention span of human politics or missions, but for cosmic time. The idea of placing such a message was both applauded and criticised. Supporters saw it as a noble gesture, a way for humanity to step beyond itself and declare its presence to the universe. Critics, however, worried that such messages might reveal our location to hostile civilizations. Some argued that announcing our existence could be dangerous. Carl Sagan and others countered that Earth has already been broadcasting radio signals for decades, and that any civilization advanced enough to intercept Pioneer would already be capable of detecting our planet. The plaque was less an announcement and more a symbol, a token of hope and curiosity. Linda Salzman Sagan, who created the artwork of the figures, faced an unusual challenge in depicting human beings. She had to draw them in a way that was recognizable, neutral, and culturally simple. The decision to depict them nude was not meant to be provocative, but to show human anatomy without cultural decoration. Even so, at the time, some critics in the United States complained about nudity being sent into space. Newspapers debated whether it was appropriate, yet the design persisted, and today it is seen as an honest and straightforward depiction of humanity. The choice of the raised hand of the man was debated as well. Was it universal enough to be seen as greeting? Could it be mistaken as aggression? The decision was that some gesture was better than none, and the raised hand might at least indicate intentionality, that the figures were aware and conscious beings. By showing both a male and female, the plaque also conveyed sexual dimorphism, the fact that humans come in two main sexes, which was important for conveying biological reproduction. The absence of children was deliberate to avoid overcrowding the small space, though in truth it left out the concept of family or social structures. The designers had to balance clarity with brevity. When the plaques left Earth aboard their spacecraft, few people realized how long these messages might endure compared to our own civilizations. Human cities rise and fall within centuries, monuments crumble within thousands of years, but the Pioneer plaques might drift for millions or even billions of years. Long after human languages have changed beyond recognition, after continents have shifted, after our species itself may have evolved or even disappeared, these small metal plates could still exist, unaltered, waiting in the silent darkness. One striking thought about the Pioneer plaques is that they may never be found. The universe is vast beyond imagination, and the chance of a small spacecraft encountering another civilization is incredibly small. They are more likely to wander endlessly, alone, yet even if they are never read, their creation had meaning for humanity itself. They represented a shift in perspective, a willingness to think on scales beyond a single lifetime or a single planet. They asked us to imagine ourselves as part of the galaxy, not just as inhabitants of one world. The trajectories of Pioneer 10 and 11 carry them outward in different directions. Pioneer 10, after its encounter with Jupiter, headed outward toward the constellation Taurus. Should it continue unimpeded, it will pass near a star called Aldebaran, the red eye of the bull, though not for about 2 million years. Pioneer 11, after visiting Saturn, headed toward the constellation Aquila, where it may pass near a distant star system in about 4 million years. These are unimaginable timescales, far beyond the lifespan of civilizations. The spacecraft are like bottles thrown into an endless cosmic ocean, drifting on currents of gravity and chance. Though the plaques were the first of their kind, they were not the last. Their creation inspired later efforts, most famously the Voyager Golden Records, launched a few years later on Voyager 1 and Voyager 2. Where the Pioneer plaques carried a simple engraved message, the Voyager records carried actual sounds and images from Earth encoded onto a phonograph record. The plaques were the first step, the first time humanity dared to send something of itself outward with the hope, however slim, of contact. When one considers the Pioneer plaques, one is struck by the blending of science and art. The pulsar map and hydrogen diagram are technical, requiring advanced understanding to interpret. But the human figures are artistic, requiring empathy and imagination to grasp. Together, they reflect both sides of humanity, the rational, mathematical mind and the expressive, symbolic spirit. They are not just instructions, but also a gesture of openness, a reaching out. The plaques also raise questions about what it means to represent humanity. Two figures can hardly capture the diversity of our species. They are simplified, schematic, and inevitably reflect the biases of the designers. The figures are drawn as average humans, but they cannot show the richness of cultures, languages, histories, or emotions. Some have criticized this as reductionist, as if humanity could be summarized by two outlines and a map. Yet given the constraints, it was perhaps the only way to convey something universal without drowning in complexity. The cultural reaction at the time was mixed, but with hindsight the plaques are seen with more reverence. They belong to a category of human artifacts that reach beyond immediate utility. Like cave paintings tens of thousands of years old, they are attempts to speak across time. But instead of speaking to descendants on Earth, they speak to unknown others across the stars. Their audience may never arrive, but their intent remains powerful. The endurance of the plaques themselves is another fascinating element. In the vacuum of space, with no atmosphere, no weather, no oxygen to corrode them, the aluminum plates could survive for eons. Micrometeoroid impacts may scar them, cosmic radiation may darken them, but the engravings cut into the metal may still be legible long after all traces of human civilization are gone from Earth. If Earth were to suffer catastrophe, if all records were destroyed, the plaques would remain as silent testimony. One can imagine a distant future where some travelers, alien or even human descendants, stumble across a derelict spacecraft drifting between stars. They approach, curious, and find bolted to its frame a small metal plate with strange engravings. They study the diagrams, the pulsars, the solar system, the figures. They realize that these were beings that once lived on a small world around a yellow star. They recognize the raised hand as something intentional, perhaps even as a greeting. In that moment, the plaques would fulfill their purpose, to connect across the gulf of space and time. The Arecibo message was created in the year 1974, at a time when humanity was just beginning to stretch its imagination beyond the limits of Earth, and to think of how we might announce our presence to the wider universe. This signal was not a random transmission, but a carefully prepared message, designed by a group of scientists who wanted to show that we were capable of both advanced thinking and advanced technology. It was broadcast from the Arecibo Observatory in Puerto Rico, which at that time was the largest and most powerful radio telescope in the world. The observatory itself was a giant dish stretching more than 300 meters across, nestled in a natural limestone sinkhole surrounded by lush hills. For decades, it had been one of humanity's ears to the cosmos, listening for faint whispers from distant galaxies, pulsars, and planets. But on that particular day in November of 1974, the dish became a mouth instead of an ear. Instead of simply listening, it sent out a voice of its own, a signal that would travel across space for tens of thousands of years. The event took place during the dedication of an upgrade to the telescope. Scientists including Frank Drake, who was already famous for his work in the search for extraterrestrial intelligence, and Carl Sagan, who later became one of the most beloved popularizers of science, collaborated on the message. Their goal was not only to test the capabilities of the observatory, but also to create a symbolic gesture, something that could demonstrate what humanity might say if we ever had the chance to send a deliberate greeting to other intelligent beings in the universe. It was not expected that the signal would actually be received or answered, because it was sent toward a cluster of stars known as Messier 13, or M13, which is more than 25,000 light-years away from Earth. Even if the message were to reach a planet orbiting one of those stars, and even if there were intelligent beings there to hear it, any reply would not return until more than 50,000 years had passed. In other words, this was not really a conversation, but more like placing a message in a bottle and casting it into a cosmic ocean, knowing that the waves might carry it somewhere, but that we would never know where or when. The message itself was transmitted as a series of radio pulses. These pulses formed a binary code, made up of ones and zeros, which is the simplest and most universal kind of language that can be imagined. The entire message was 1,679 bits long. That number was not chosen at random, but very carefully. 1,679 is the product of two prime numbers, 23 and 73. This means that if someone were to receive the string of bits and try to arrange them into a rectangular grid, the only possible ways would be either 23 rows with 73 columns or 73 rows with 23 columns. When arranged correctly, the grid would reveal patterns that make pictures. The scientists hoped that intelligent beings, even if they had no knowledge of human languages, might understand the logic of prime numbers and might therefore reconstruct the message into its intended form. When arranged, the Arecibo message contained several parts. At the top was a sequence representing the numbers 1 through 10, written in binary. This was meant to show that the senders understood mathematics and could use a logical numeric system. Below the numbers was information about the elements most important for life on Earth, such as hydrogen, carbon, nitrogen, oxygen, and phosphorus. These were written in a way that showed their atomic numbers. Beneath this was a section describing the basic building blocks of DNA, the long molecule that contains the genetic instructions for life. The message included a diagram of the double helix structure and even indicated the number of nucleotides in the human genome. After this was a representation of a human being, with the figure of a man standing with arms and legs outstretched. Next to him was a number giving the average height of humans. Beside the human figure was a representation of the solar system, showing the sun and the planets, with Earth highlighted to indicate where we come from. At the bottom of the message was a sketch of the Arecibo telescope itself, including its size in relation to the transmission wavelength, a kind of cosmic signature that said not only who we are but also how we were able to send this signal. The decision to include these elements was both practical and symbolic. Numbers and prime factors are thought to be universal truths that any intelligent civilization would recognize. Chemical elements like hydrogen and carbon are not unique to Earth, but are found throughout the universe, so the use of them as a basis for communication seemed logical. The inclusion of DNA was meant to express that life on our planet is based on chemistry that can be described and understood. The human figure was a bold gesture, showing not only our intellectual side but also our physical form, and the depiction of the solar system gave a clue about our location. All of this was compressed into less than 2,000 bits, a package small in size but monumental in meaning. The actual broadcast of the message lasted only about 3 minutes. In those 3 minutes, humanity sent out a signal of such power that, if there had been a radio receiver as strong as ours within the target cluster, it could have been detected with ease. The signal spread out as it travelled, but in that brief moment it was stronger than the background noise of space by many orders of magnitude. It was like shining a powerful flashlight into the darkness, a beam of knowledge directed at the stars. The people who were present at the observatory that day understood the weight of what they were doing. They were not just celebrating a scientific instrument, they were taking part in an act of cosmic communication. Even though the scientists knew that the message was unlikely to be answered, the gesture had profound importance. It was a declaration of curiosity, of hope, and of the desire to connect beyond our small world. It also raised questions about how we should represent ourselves. For example, the message showed a man as the human figure, though some critics later pointed out that this might have been too narrow a symbol of humanity. Others wondered if the technical details such as the structure of DNA were too specific or too difficult for aliens to understand. But the intent was clear, to offer a sample of what we are, not just in appearance, but in knowledge and in our place in the cosmos. The Arecibo message has continued to spark imagination for decades. It inspired writers, artists, filmmakers, and thinkers who wondered what it would mean for such a signal to be received. Would aliens recognize it as a greeting? Would they understand the mathematical and chemical language? Or would it appear to them as nothing more than a meaningless pattern of noise? These questions became part of the broader conversation about whether humanity should actively send messages into space or simply listen. Some argued that sending signals could be dangerous because we do not know what kind of civilizations might be out there. Others believed that communication is part of what makes us human, and that to remain silent would be to deny our deepest instincts to explore and to share. The location chosen for the broadcast was not random either. Messier 13, the globular cluster toward which the signal was sent, is a dazzling collection of hundreds of thousands of stars, packed tightly together like glittering jewels in a ball. It lies in the constellation of Hercules and can be seen with binoculars or a small telescope as a fuzzy patch of light. Its great distance means that the signal will take tens of thousands of years just to reach it, and by then the stars themselves may have shifted positions. This adds to the symbolic nature of the message. It was less about expecting a reply and more about marking a moment in human history when we declared that we were ready to speak. For many years after 1974, Arecibo discovered new pulsars, mapped the surfaces of planets, studied the movements of asteroids, and helped track signals from deep space. It became a cultural icon as well, appearing in films, television shows, and books. Its massive dish, spread across the jungle of Puerto Rico, became a symbol of humanity's reach into the cosmos. Sadly, in the year 2020, the Great Dish collapsed after cables failed, ending its decades of service.